On October 3rd, 2025, something unprecedented will happen in our solar system. For the first time in recorded history, an interstellar visitor will sweep past Mars at a distance so close it could fundamentally alter everything we thought we knew about planetary safety. 3I Atlas, this mysterious wanderer from beyond the stars, isn't just another space rock drifting through the cosmic void. It's a 200-meter-long enigma that's been defying our models and challenging our assumptions since the moment we discovered it. What makes this encounter truly terrifying isn't just the proximity. It's the fact that 3I Atlas has been behaving like no comet we've ever observed. Massive gas emissions when it should be dormant. Brightness flares that appear without warning. Chemical signatures that don't match anything in our solar system. This thing has been throwing cosmic tantrums for months, and now it's heading straight for Mars at speeds that make bullets look sluggish. But here's what keeps planetary scientists awake at night. We're flying blind during the most critical moments. Solar conjunction means our ability to observe this encounter will be severely limited right when things could get catastrophic. It's like trying to monitor a potential disaster through a keyhole while wearing a blindfold. The worst-case scenarios range from direct impacts that create 30-kilometer craters to atmospheric shock waves that could permanently alter Mars's climate. We're talking about contamination from alien chemistry, electromagnetic storms that cripple our spacecraft, and orbital chaos that could turn Mars into a cosmic shooting gallery for decades to come. But the truly terrifying possibility might not be physical destruction at all. It might be something far more subtle and infinitely more dangerous. Welcome to the most comprehensive analysis of what could happen when an interstellar visitor meets the red planet. By the time we're finished, you'll understand why October 3rd, 2025 might be remembered as the day everything changed for humanity's plans to explore Mars. Let's dive into the nightmare scenarios that official agencies don't want to discuss publicly. Part 1. The approaching storm. To understand why 3I Atlas represents such an unprecedented threat, we need to grasp just how alien this visitor truly is. When astronomers first detected it racing through our solar system, they immediately recognized something was fundamentally wrong with their models. This wasn't behaving like the well-mannered comets we're used to studying. Standard comets follow predictable patterns as they approach the sun. They warm up gradually, releasing water vapor and creating those beautiful tails we see in photographs. Their brightness increases steadily. Their emissions follow established chemical signatures, and their behavior can be calculated months or years in advance. 3I Atlas has violated every single one of these expectations. The object has been generating a carbon dioxide coma of absolutely staggering proportions. We're talking about a gas cloud that extends millions of kilometers in every direction, far larger than anything we've observed from objects of similar size. Most disturbing, it's been doing this while still incredibly far from the sun, at distances where conventional comets should remain completely dormant. The brightness surges have been equally baffling. Multiple observatories have recorded sudden flare-ups that appear without warning and fade just as mysteriously. These aren't the gentle, predictable changes we expect from a chunk of ice slowly warming in sunlight. These are violent, chaotic outbursts that suggest something fundamentally unstable about the object's internal structure. Spectroscopic analysis has revealed chemical signatures that don't match any formation environment in our solar system. The organic compounds detected in 3I Atlas's emissions show characteristics that could only have formed around a different type of star, under conditions we've never directly observed. This thing is carrying alien chemistry forged in stellar environments that might not even exist anymore. But perhaps most unsettling is the object's rotation. Natural asteroids and comets tumble chaotically through space, their spin rates affected by collisions and outgassing events over millions of years. 3I Atlas, however, maintains an eerily stable rotation pattern that seems almost controlled. The brightness variations follow such regular cycles that some researchers have quietly begun questioning whether we're dealing with natural processes at all. NASA's trajectory calculations place 3I Atlas at approximately 30 million kilometers from Mars during closest approach. In cosmic terms, that's uncomfortably close. For perspective, that's only about 75 times the distance from Earth to our Moon. When you're dealing with an object that's already demonstrated unpredictable behavior, that proximity becomes genuinely alarming. The European Space Agency has been tracking this encounter with the kind of nervous precision usually reserved for diffusing explosive devices. Their models attempt to predict the object's behavior during the Mars flyby, but every simulation comes with enormous error bars because 3I Atlas keeps defying the fundamental assumptions that make such calculations possible. What makes this situation particularly nerve-wracking is the timing. Solar conjunction occurs when Mars, the Sun, and Earth align in such a way that our ability to observe the red planet becomes severely compromised. For several weeks around the October 3rd encounter, our monitoring capabilities will be dramatically reduced right when we need them most. Think about the implications of this timing. Just when 3I Atlas reaches its most critical phase, just when its proximity to Mars could trigger the most significant events, we'll be essentially flying blind. It's as if the universe conspired to hide the most important moments of this cosmic encounter from human observation. Ground-based telescopes will struggle with solar interference. Space-based observatories will face communication delays and positioning challenges. Even our most sophisticated monitoring systems will be operating under severe constraints precisely when clear, continuous observation becomes most crucial for understanding what's happening. The scientific community has been walking a delicate balance between professional skepticism and barely contained concern. Behind closed doors, researchers are discussing possibilities that they're reluctant to address in public forums. The rapid activity changes, the massive gas emissions, the unexplained brightness flares, all of these could be warning signs of impending fragmentation. When comets fragment, they don't do so gently. The process typically involves violent breakup events that can scatter debris across millions of kilometers of space. If 3I Atlas were to undergo such fragmentation during its approach to Mars, the consequences could be catastrophic on a scale we've never had to consider before. Imagine kilometer-sized chunks of ancient ice and rock, each carrying the momentum of interstellar travel, suddenly liberated from their parent body within striking distance of Mars. Some fragments might continue on harmless trajectories toward the outer solar system. Others could find themselves deflected by Mars gravity into collision courses with the planet itself. The Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter represent humanity's electronic presence around the red planet. These sophisticated spacecraft were designed to study Mars under normal conditions, not to survive cosmic catastrophes. Their delicate instruments, communication systems, and solar panels could be overwhelmed by debris impacts or electromagnetic interference from fragmentation events. But the spacecraft represent just the beginning of our concerns. Mars itself, despite surviving 4 billion years of cosmic bombardment, has never faced anything quite like 3I Atlas. The planet's thin atmosphere provides virtually no protection against high-velocity impacts. Its weak magnetic field offers minimal shielding against electromagnetic effects. In many ways, Mars stands naked before whatever cosmic forces this interstellar visitor might unleash. The impact scenarios alone are enough to give planetary scientists nightmares. A fragment just 100 meters across, traveling at interstellar velocities, would deliver kinetic energy equivalent to thousands of nuclear weapons. The resulting crater would span several kilometers, ejecting millions of tons of Martian soil into the thin atmosphere, and potentially triggering planet-wide dust storms that could persist for years. But direct impacts might not even represent the worst-case scenario. Mars's atmosphere, though thin, is still complex enough to respond dramatically to sudden energy inputs. Electromagnetic effects from 3I Atlas could disrupt the planet's ionosphere, creating communication blackouts and auroral displays that dwarf anything previously observed. The chemical contamination from alien organic compounds could alter Mars' atmospheric chemistry in ways that persist for decades. As we approach October 3rd, the tension within the astronomical community continues building. Every new observation of 3I Atlas brings fresh puzzles rather than reassuring answers. The object's behavior remains as unpredictable as ever. Its emissions continue following patterns that don't match our models, and its approach toward Mars proceeds with the inevitability of orbital mechanics. The question that haunts every researcher involved in monitoring this encounter is simple yet terrifying. What happens when an interstellar visitor that doesn't follow our rules meets a planet that has no defense against cosmic chaos? The answer will unfold over the coming days, and it might reshape everything we thought we understood about planetary safety in our cosmic neighborhood. In our next segment, we'll examine the specific impact scenarios that could transform Mars from humanity's next frontier into a cosmic wasteland. The physics of these collisions are as fascinating as they are horrifying, and the consequences could echo through the solar system for generations to come. Part 2. When worlds collide. The mathematics of cosmic destruction follow laws that are both beautiful and terrifying. When we calculate the probability of 3I Atlas actually striking Mars, the initial numbers seem almost comforting. Direct collision odds hover around 1 in several million, the kind of astronomical longshot that should let us sleep peacefully at night. But here's the problem with cosmic roulette. The house always has ways of changing the odds that we never see coming. What keeps planetary defense specialists reaching for their emergency protocols isn't the main body of 3I Atlas. It's what happens if this interstellar wanderer decides to fall apart at precisely the wrong moment. Picture an object that's held itself together through 30,000 years of cosmic radiation, temperature extremes, and gravitational stress, only to finally succumb to structural failure just as it reaches Mars' doorstep. The fragmentation physics are as fascinating as they are nightmarish. When comets break apart, they don't simply crack like eggs hitting pavement. The process involves explosive decompression as internal gases suddenly find pathways to escape. Chunks of ancient ice and rock get hurled in random directions, each piece carrying momentum that could turn it into a planet-killing projectile. Now imagine this happening not in the safe depths of interstellar space, but within Mars's gravitational sphere of influence. The parent body might continue on its predicted trajectory, passing harmlessly by the red planet, while astronomers breathe collective sighs of relief. But the fragments would write their own rules, following chaotic paths that no computer model could predict with certainty. A piece just 200 meters across, roughly the size of a city block, would arrive at Mars, traveling faster than anything in our solar system's natural inventory. The kinetic energy involved would equal thousands of nuclear weapons detonating simultaneously. But unlike nuclear explosions, which release their energy gradually over seconds, an impact delivers its entire payload instantaneously to a single point on the planetary surface. Mars's thin atmosphere offers virtually no protection against such cosmic violence. Earth's thick atmospheric blanket can burn up smaller objects and slow larger ones, absorbing some of the destructive energy before impact. Mars might as well be completely naked to cosmic assault. Every joule of kinetic energy gets delivered directly to the surface with undiluted fury. The immediate crater would span 15 to 20 kilometers, but that's just the beginning of Mars's ordeal. The impact would excavate millions of tons of ancient Martian rock, some of it dating back to the planet's formation over 4 billion years ago. This material would be hurled high into the atmosphere at velocities exceeding escape velocity, creating a temporary ring of debris around the planet. What comes up must come down, and when it does, Mars would experience something unprecedented in its geological record. Secondary impacts from falling debris would pepper the planet's surface for hours or even days after the initial collision. Each piece of ejected material would strike with enough force to create its own crater, turning vast regions of the Martian surface into a cosmic shooting gallery. The atmospheric effects would be immediate and dramatic. Mars's delicate climate system, which has remained relatively stable for millions of years, would be thrown into absolute chaos. The dust cloud generated by the impact would be unlike anything we've observed in the planet's seasonal dust storm cycles. Instead of the predictable weather patterns that Mars rovers have documented for decades, we'd be witnessing the birth of a planetary dust hurricane that could persist for years. Temperature swings would become extreme as the dust-laden atmosphere alternately blocked incoming solar radiation and trapped surface heat. The thin atmospheric envelope that currently allows some solar energy to reach the surface would become an opaque barrier, plunging surface temperatures far below their current levels. Mars would experience its own version of nuclear winter, triggered not by human warfare, but by cosmic accident. But let's escalate this scenario to its most horrifying logical conclusion. What if 3I Atlas doesn't just produce one fragment, but dozens? What if the object completely disintegrates during its approach, creating a swarm of projectiles that turn Mars into the solar system's largest target practice range? Multiple impacts would create overlapping shockwaves that could literally shake the planet. Mars' two small moons, Phobos and Deimos, orbit close enough to the surface that they could be affected by debris from large impacts. These irregularly shaped chunks of rock are already unstable. Phobos is gradually spiraling inward toward an eventual collision with Mars, though not for another 50 million years under normal circumstances. A major impact event could dramatically accelerate this timeline. If debris from surface collisions were to strike Phobos with sufficient force, or if shockwaves through Mars itself were to alter the moon's orbital mechanics, we could witness the destruction of a moon in real time. The fragments from such an event would create a debris ring around Mars, but not the elegant, stable rings of Saturn. Instead, we'd be looking at a chaotic cloud of rocky chunks that would make Mars' orbit hazardous for spacecraft operations for centuries to come. The electromagnetic consequences would be equally devastating. Impact events of this magnitude generate intense electromagnetic pulses as the expanding fireball interacts with Mars' weak magnetic field. These pulses could induce damaging currents in any electronic systems operating around the planet, potentially crippling our robotic explorers just when we need them most to document what's happening. Our Mars orbiters, the Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, were designed to study the planet under normal conditions. They carry sensitive instruments calibrated for routine atmospheric and surface observations, not for surviving electromagnetic chaos and debris bombardment. Star trackers could lose lock on their reference points. Communication systems could be overwhelmed by interference. Solar panels could be damaged by high-velocity particles. On the surface, the situation would be even more dire. The Perseverance and Curiosity rovers, along with any future human missions, would face radiation levels that spike dramatically as impact events excavate radioactive materials from deep within Mars' crust. The thin, atmospheric protection that currently shields the surface from the worst cosmic radiation would become saturated with charged particles, creating hazardous conditions that could persist for decades. But perhaps the most unsettling aspect of multiple impact scenarios is how they would cascade through Mars's entire system. The planet's climate, geology, and electromagnetic environment are all interconnected in ways we're still learning to understand. Major disruptions to any one system could trigger chain reactions that fundamentally alter Mars' character as a world. The dust storms alone could reshape the planet's surface features. Wind patterns that have remained stable for millions of years would be disrupted by temperature differentials created by impact craters and debris fields. Ancient geological formations that have survived since Mars' youth could be buried under layers of impact ejecta, erasing billions of years of planetary history in a matter of hours. Water ice, both at the polar caps and in subsurface deposits, would be affected by the dramatic temperature swings. Some regions might experience temporary warming as atmospheric dust traps heat, leading to unexpected sublimation of ice deposits. Other areas could freeze permanently as reduced solar radiation creates new permafrost regions in places where water had remained liquid in subsurface aquifers. The implications for future Mars exploration would be catastrophic. Every landing site chosen for upcoming missions would need to be re-evaluated based on new crater fields, altered atmospheric conditions, and changed radiation environments. The carefully planned Artemis Mars missions could face delays measured in decades rather than years, as scientists struggle to understand the new planetary environment that 3I Atlas had created. Most heartbreaking of all would be the loss of scientific opportunity. Mars has served as our natural laboratory for understanding planetary evolution, climate change, and the potential for life beyond Earth. The rovers and landers that have spent years carefully analyzing Martian soil samples would be buried under impact debris, their discoveries lost to cosmic violence. The geological record that has taken decades to decipher would be scrambled beyond recognition. Yet even as we contemplate these scenarios of planetary destruction, we must remember that direct impacts represent only one category of potential catastrophe. Mars' thin atmosphere and weak magnetic field make it vulnerable to effects that might not even require physical contact with 3I Atlas or its fragments. In our next segment, we'll explore how this interstellar visitor could transform Mars through forces that operate at the speed of light, creating chaos without ever actually touching the planet's surface. Part 3. The Invisible Assault. Forget everything you think you know about cosmic impacts. The most devastating attack that 3I Atlas could launch against Mars might never involve a single grain of debris actually touching the planet's surface. Instead, we're looking at something far more insidious and potentially permanent. An electromagnetic and particle bombardment that could fundamentally rewire Mars's entire atmospheric and electrical environment. Mars stands defenseless against this type of assault in ways that should terrify anyone who understands planetary physics. Unlike Earth, which wraps itself in a protective magnetic cocoon that deflects most charged particles, Mars lost its global magnetic field billions of years ago. What remains are scattered magnetic anomalies, cosmic scars that serve as tombstones for the planet's former protective shield. This magnetic nakedness makes Mars exquisitely vulnerable to effects that Earth's magnetosphere would deflect without breaking a sweat. When 3I Atlas sweeps past Mars trailing its enormous carbon dioxide coma and potentially shedding charged particles, it won't be delivering a conventional shockwave. Instead, we're looking at an electromagnetic cascade that could alter Mars' atmospheric chemistry and electrical environment for years or even decades. Picture 3I Atlas as it approaches Mars, its nucleus venting ionized gases in the chaotic bursts we've been documenting for months. Each outburst creates expanding clouds of plasma that interact with the solar wind in ways our models struggle to predict. As this ionized cocktail encounters Mars's weak magnetic field remnants, it doesn't simply bounce off or pass through. It penetrates, swirls, and creates electromagnetic eddies that can persist long after the comet itself has continued on its trajectory. The immediate effect would be a dramatic enhancement of Mars' normally faint auroral displays. Instead of the subtle localized glows that Mars occasionally produces, we might witness planet-wide light shows as charged particles from 3I Atlas cascade into the upper atmosphere. But these wouldn't be the gentle, romantic displays that grace Earth's polar regions. They'd be angry, chaotic storms of light that could interfere with radio communications and potentially damage sensitive electronic equipment. The visible effects, spectacular as they might be, represent only the tip of an electromagnetic iceberg. The real chaos would unfold in Mars' ionosphere, that electrically charged layer of the upper atmosphere that our orbiting spacecraft depend on for communications. As charged particles from 3I Atlas interact with this delicate region, they could create radio blackout conditions that persist for weeks or months. Think about the implications for our robotic explorers. Mars rovers have grown accustomed to reliable communication windows with Earth, carefully scheduled sessions where they upload their discoveries and download new instructions. An ionospheric disruption could sever these digital lifelines, leaving billion-dollar robots effectively stranded on an alien world, unable to report their status or receive guidance from their human controllers. The electromagnetic chaos wouldn't stop at the ionosphere. Mars' thin atmosphere makes it particularly susceptible to electrostatic effects that would barely register on a world with robust atmospheric protection. As 3I Atlas debris field interacts with the Martian environment, it could create conditions similar to the massive dust devils that already plague the planet, but supercharged with electrical potential. Imagine dust storms where individual particles carry significant electrical charges, creating lightning displays that dwarf anything Earth has ever witnessed. These wouldn't be the relatively gentle static discharges we observe in terrestrial thunderstorms. We're talking about violent arcs of electrical energy capable of damaging surface equipment and creating radio frequency interference that would make communication with Earth virtually impossible. The scenario becomes genuinely alarming when we consider Mars's propensity for global dust storms. These planet-wide tempests can begin from seemingly minor triggers. A small temperature differential here, a pressure change there. The electromagnetic chaos from 3I Atlas passage could provide exactly the kind of trigger needed to push Mars's atmospheric system over the edge into one of these global catastrophes. But here's where atmospheric physics gets truly disturbing. What if 3I Atlas passage doesn't just trigger a conventional dust storm, but creates something entirely new in the annals of planetary meteorology? What if the combination of charged particles from the comet's environment and Mars's existing atmospheric dynamics creates a feedback loop that becomes self-sustaining? Picture this nightmare scenario. 3I Atlas charged debris creates initial electromagnetic disturbances in Mars's upper atmosphere. These disturbances generate static electricity in the lower atmosphere, which charges dust particles and makes them more likely to become airborne. The increased dust loading alters the planet's energy balance, creating temperature and pressure differentials that sustain the storm. Meanwhile, the charged dust particles continue to interact with Mars's remnant magnetic fields, perpetuating the electromagnetic chaos. The result would be a planet trapped in a quasi-permanent state of electromagnetic and meteorological turmoil. A feedback loop from hell that could persist for years after 3I Atlas has continued its journey toward the outer solar system. Mars would become a world where dust storms never end, where radio communications are sporadic at best, and where the radiation environment becomes so chaotic that even our hardiest robotic explorers might succumb to electronic failures. NASA's spacecraft designers have anticipated many challenges for Mars operations, but they've never had to contend with a planet-wide electromagnetic tornado. The Mars Reconnaissance Orbiter's high-gain antenna might find itself constantly fighting interference from charged dust clouds. MAVEN's particle detectors, designed to study gentle solar wind interactions with Mars' upper atmosphere, could be overwhelmed by the chaotic particle environment created by 3I Atlas passage. The public relations nightmare would be immediate and profound. As images from Mars become sporadic and communication windows disappear, speculation would run wild. Social media would explode with theories about what's really happening to our robotic ambassadors on the red planet. Official explanations about ionospheric disturbances and electromagnetic interference would be drowned out by more sensational narratives about cosmic catastrophes. But perhaps the most unsettling aspect of this scenario is how it would be misunderstood by the general public. Mars wouldn't actually be burning in any conventional sense. Carbon dioxide doesn't support combustion the way oxygen does. But the global auroral displays, the constant lightning from charged dust storms, and the eerie electromagnetic phenomena would create visual effects that could easily be misinterpreted as planetary conflagration. The scientific community would find itself in the awkward position of trying to explain that Mars hasn't actually ignited, while simultaneously acknowledging that the planet has indeed become temporarily uninhabitable for human exploration. The distinction between chemically burning and electromagnetically chaotic would be lost on a public already primed by decades of disaster movies to expect the worst possible interpretations. Yet even as we contemplate these electromagnetic nightmares, we must acknowledge that atmospheric chaos might not represent the ultimate worst-case scenario. What if 3I Atlas brings something to Mars that's far more persistent than electromagnetic storms, far more insidious than charged dust clouds? What if the real threat isn't physical or electrical, but biological? A contamination from another star system that could fundamentally alter not just Mars' immediate future, but humanity's entire relationship with the red planet. The contamination scenario we're about to explore operates on timescales that make electromagnetic storms look like brief summer squalls, introducing variables that could affect Mars exploration for centuries to come. Part 4. The Alien Chemistry Invasion. The concept of panspermia has haunted astrobiologists for decades. The idea that life could hitchhike between worlds on cosmic debris, spreading through the galaxy like seeds on an interstellar wind. But when that debris originates from an entirely different star system, carrying chemistry that evolved under alien conditions, the implications become profound enough to fundamentally reshape our understanding of planetary contamination. 3I Atlas presents us with a scenario that no planetary protection protocol ever anticipated. This interstellar wanderer has spent tens of thousands of years traveling through the void between stars, its nucleus serving as a cosmic deep freeze for whatever molecular cargo it accumulated during formation around a distant alien sun. The massive carbon dioxide emissions we've been tracking aren't just unusual outgassing patterns. They're potential delivery systems for organic compounds that have never existed anywhere in our solar system. The James Webb Space Telescope's spectroscopic analysis has detected signatures that go far beyond simple carbon dioxide and water vapor. Buried in the infrared data are absorption lines that correspond to complex organic molecules, chemical structures that formed under the unique conditions of another stellar environment. These aren't the familiar carbon compounds we find in Earth's atmosphere or even in typical solar system comets. These are alien organics, forged in the crucible of a star whose properties we can only guess at. Carbon dioxide, it turns out, isn't just a waste gas when it comes to interstellar chemistry. It's an excellent solvent capable of stabilizing complex molecular structures across the temperature and pressure ranges that 3I Atlas has experienced during its journey. The comet's coma isn't just venting gas. It's potentially dispersing a chemical library that contains the molecular fingerprints of processes that occurred billions of years ago around a star we'll never see. But here's where the contamination scenario becomes genuinely terrifying. Unlike the electromagnetic effects we discussed earlier, which would fade as conditions return to normal, chemical contamination could prove essentially permanent on human timescales. Exotic organic molecules from 3I Atlas could integrate with Mars's regolith, alter the planet's atmospheric chemistry, and create persistent changes that affect every future landing site for centuries to come. Picture this nightmare unfolding as 3I Atlas sweeps past Mars on October 3rd. The comet's massive coma doesn't just create pretty auroral displays. It deposits trace amounts of alien organic compounds across vast regions of the Martian surface. These molecules, evolved under conditions that never existed in our solar system, begin interacting with Martian soil in ways that our models can't predict. The initial contamination might seem minor, a few parts per billion of exotic organics scattered across millions of square kilometers of Martian terrain. But chemistry has a way of amplifying small effects into large consequences. These alien compounds could catalyze reactions that alter the fundamental chemistry of Martian regolith, creating cascading changes that spread far beyond the initial deposition zones. Mars exploration has always been driven by one overarching question: did life ever exist on the red planet? The sophisticated instruments currently being developed for future sample return missions are designed to detect the subtlest chemical signatures that might indicate past or present biological processes. But what happens when those same instruments encounter organic molecules that originated from 3I Atlas? How do we distinguish between indigenous Martian biochemistry and contamination from an interstellar visitor? The scientific implications could set back our understanding of Mars by decades. Every soil sample, every atmospheric measurement, every search for biosignatures would be complicated by the presence of alien organics that we don't understand and can't control. Future missions might find themselves studying the chemistry of another star system rather than the geology of Mars itself. The contamination scenario becomes even more complex when we consider atmospheric distribution. Mars is notorious for its global dust storms, weather systems that can engulf the entire planet and redistribute surface materials across vast distances. If 3I Atlas deposits alien organics on the Martian surface, these compounds wouldn't stay put. They'd become airborne during the next major dust storm, spreading contamination to every corner of the planet within a matter of weeks. NASA's current Mars exploration timeline assumes that the red planet represents a relatively predictable environment where life support systems can function reliably and where in situ resource utilization can provide the water, oxygen, and fuel needed for human missions. Organic contamination from 3I Atlas could undermine these assumptions completely. Imagine trying to extract water from Martian ice deposits that have been contaminated with alien organic compounds. The purification systems designed for typical Martian chemistry might not be able to handle exotic molecules that follow different chemical rules. Atmospheric processes designed to convert carbon dioxide into oxygen could be fouled by trace organics that interfere with catalytic reactions. Even the psychological impact on human crews could be devastating. The timeline for understanding these effects stretches far beyond typical mission planning horizons. Unlike impact craters or electromagnetic storms, which reveal their consequences relatively quickly, chemical contamination operates on much longer timescales. We might not fully comprehend what 3I Atlas has done to Mars until well into the 2040s or beyond, when detailed chemical analysis reveals the full extent of molecular alterations to the Martian environment. International space law provides little guidance for scenarios involving contamination from interstellar objects. The Outer Space Treaty and subsequent agreements were crafted with human-caused contamination in mind, not cosmic delivery of alien chemistry. If 3I Atlas does contaminate Mars, there's no clear legal framework for determining responsibility, coordinating international response, or managing the long-term consequences for Mars exploration programs. But perhaps most disturbing is the possibility of false positives in our search for Martian life. The organic compounds that 3I Atlas might deposit could mimic some characteristics of biological activity while being entirely abiotic in origin. Future life detection experiments might register positive results that actually represent contamination from an interstellar visitor rather than evidence of indigenous Martian biology. The contamination doesn't have to be biological to be devastating. Self-organizing chemical systems, complex organic networks that exhibit some characteristics of living systems without actually being alive, could prove equally disruptive. These pseudo-biological processes might consume resources, alter local chemistry, and spread through environmental mechanisms that make them virtually impossible to contain or reverse. Environmental remediation techniques that work on Earth depend on biological systems that can break down contaminants over time. Mars lacks these biological cleaning mechanisms. Alien organic compounds that prove persistent in the Martian environment could remain active for geological timescales, fundamentally altering the planet's chemistry in ways that affect every future human mission. The economic implications alone could derail Mars colonization efforts for generations. Private space companies that have invested billions in Mars transportation and habitat systems would find their business models undermined by contamination scenarios they never anticipated. Mission costs would skyrocket, as every system requires redesign to handle exotic chemistry that doesn't exist in any Earth-based testing facility. But contamination represents just one category of long-term threat that 3I Atlas could pose to the Martian system. The gravitational dynamics of this encounter could set in motion changes that won't become apparent for years or decades, but which could ultimately prove even more catastrophic than chemical contamination. In our next segment, we'll explore how this interstellar visitor could destabilize the delicate orbital relationships that have kept the Martian system stable for billions of years, creating cascading effects that could turn Mars into a cosmic shooting gallery for centuries to come. Part 5. The orbital domino effect. The gravitational dance between celestial bodies operates according to mathematical principles that seem deceptively simple on the surface. Objects attract each other with forces proportional to their masses and inversely proportional to the square of the distance between them. Clean, predictable, reassuring in its cosmic reliability. But chaos theory teaches us that small influences can cascade into enormous consequences when systems exist near critical transition points. And Mars's two tiny moons, Phobos and Deimos, have been teetering on the edge of gravitational catastrophe for millions of years. Phobos, the larger and inner of Mars's two captured asteroids, is already serving a cosmic death sentence. This irregularly shaped chunk of rock orbits so close to Mars that it completes 3 full circuits around the planet every Martian day. At an altitude of just 6,000 kilometers above the surface, Phobos exists well within what astronomers call the Roche limit, that critical distance where tidal forces from the parent planet begin to overcome the moon's own gravity. Under normal circumstances, Phobos would continue its slow spiral inward for another 50 million years before finally crashing into Mars. That timeline provides comfortable breathing room for human civilization to establish itself on the red planet and develop solutions for the eventual moon crash scenario. But 3I Atlas introduces variables that could dramatically accelerate this cosmic execution schedule. The direct gravitational influence of 3I Atlas on Mars moons would be negligible at the predicted flyby distance of 30 million kilometers. We're talking about gravitational forces roughly equivalent to a large building on Earth trying to influence the moon's orbit. The mathematics simply don't support scenarios where the comet reaches out with invisible hands to directly perturb the Martian satellites. But chaos theory operates in the realm of cumulative effects and cascade failures. Phobos exists in a state of such gravitational precariousness that even minor perturbations could trigger consequences that unfold over years or decades. The moon is already showing stress fractures, parallel grooves that may represent the early stages of tidal breakup. Recent orbital analysis suggests that Phobos is literally being pulled apart by Mars' gravity, grain by grain, orbit by orbit. Now introduce 3I Atlas into this delicate gravitational ballet. The comet might not exert enough direct force to matter, but it brings something potentially more dangerous: debris. As we've established, 3I Atlas has been shedding material in chaotic bursts that don't match our models of normal comet behavior. Even tiny particles, when traveling at interstellar velocities, carry tremendous kinetic energy. A grain of sand from 3I Atlas coma, striking Phobos at 20 kilometers per second, would impact with the force of a small explosive device. Scale this up to thousands or millions of particles, and you begin to understand how a seemingly gentle cosmic encounter could become a devastating bombardment that pushes Phobos' already stressed structure beyond its breaking point. Instead of gradually disintegrating over millions of years, the moon could fragment catastrophically during or shortly after 3I Atlas passage. What has been a slow-motion cosmic demolition project spanning geological ages could become a sudden explosion of debris that fundamentally alters the Martian orbital environment within a matter of hours. But let's escalate this scenario to its most nightmarish logical conclusion. What if 3I Atlas doesn't just accelerate Phobos destruction, but creates something entirely unprecedented in our solar system? What if the encounter generates enough orbital chaos to give Mars its first ring system? The physics of planetary rings are far more complex than most people realize. Saturn's elegant bands of ice and rock represent a delicate balance between gravitational forces, particle collisions, and electromagnetic effects that took millions of years to achieve stability. A ring system created by the violent fragmentation of Phobos would be nothing like Saturn's orderly cosmic jewelry. Instead, Mars would find itself surrounded by a chaotic cloud of debris following wildly elliptical orbits. Some fragments would be large enough to pose serious hazards to spacecraft operations for centuries to come. Others would be small enough to create a persistent micrometeorite environment that could sandblast solar panels and optical instruments over time, making routine Mars orbital operations virtually impossible. The navigation challenges for future Mars missions would become nightmarish beyond current comprehension. Instead of planning trajectories around two small, predictable moons, mission planners would have to contend with thousands of fragments following unpredictable paths through Mars' orbital space. Risk assessment algorithms would struggle to calculate safe approach corridors through a three-dimensional minefield of rocky debris, moving at speeds that turn even small collisions into catastrophic events. But orbital mechanics has a cruel sense of humor when it comes to cleanup operations. Unlike terrestrial pollution, which can sometimes be remediated through human intervention, orbital debris follows the immutable laws of physics. Every collision between fragments creates more fragments, each following its own trajectory according to conservation of momentum. The process feeds on itself, creating cascade effects that can persist for geological timescales. This phenomenon, known in space operations as Kessler syndrome, represents a runaway chain reaction of orbital collisions that renders entire regions of space unusable for practical operations. We've been concerned about this scenario affecting Earth's orbital environment for decades, but Mars, with its weaker gravitational field and thinner atmosphere, might prove even more vulnerable to cascading destruction. The psychological impact on humanity's Mars colonization dreams would be profound and lasting. For generations, we've envisioned Mars as our backup planet, our cosmic life insurance policy against existential risks that could threaten Earth-based civilization. To watch that future literally fragment before our eyes would be like witnessing the destruction of our species' most cherished hopes for expansion beyond our home world. The timeline for recovery could span geological ages. Unlike atmospheric storms or chemical contamination, which operate on timescales that human technology might eventually address, orbital debris mechanics operate according to celestial laws that make human intervention virtually impossible. Fragments from Phobos destruction could continue posing hazards to Mars operations for thousands or millions of years, effectively closing the red planet to human exploration for longer than our species has existed. Yet even this orbital catastrophe scenario represents thinking too locally about 3I Atlas potential for long-term destruction. What if the October 3rd encounter at Mars represents not an endpoint, but merely the opening movement in a much longer gravitational symphony? What if the perturbations introduced by this interstellar visitor propagate outward through the solar system's interconnected web of orbital relationships, cosmic disaster to our, eventually bringing own doorstep? The mathematics of orbital perturbation theory teach us that every gravitational encounter, no matter how minor, slightly alters the trajectory of every object involved. Changes measured in millimeters per second that seem utterly insignificant in the context of planetary velocities can accumulate over time through processes of gravitational resonance and secular evolution. 3I Atlas passage near Mars will inevitably change both objects' orbits by tiny amounts. These shifts, imperceptible in the immediate aftermath, could compound over decades through resonant interactions with other solar system bodies. What begins as an imperceptible nudge could eventually grow into trajectory changes measured in thousands of kilometers, potentially bringing fragments of the encounter into Earth-threatening orbits years or decades in the future. The most immediate concern involves debris trajectories. If 3I Atlas undergoes fragmentation during its Mars encounter, the resulting fragments won't simply disappear into the outer solar system. Each piece will continue following its own modified orbit, creating what planetary defense specialists euphemistically call a persistent hazard environment for the inner solar system. Some fragments might find themselves in orbital resonances with Earth's orbit, creating periodic encounters that could persist for decades or centuries. Others might be perturbed into highly elliptical paths that bring them into the inner solar system during unpredictable time windows. The net result would be a subtle but measurable increase in the background flux of potentially hazardous objects threatening Earth, fundamentally altering the risk environment for human civilization. Our planetary defense systems, sophisticated as they've become, were calibrated to detect objects following relatively predictable orbits within our solar system. 3I Atlas fragments arriving on chaotic trajectories influenced by interstellar velocities and multiple gravitational encounters might not fit standard detection profiles. Their approach angles could be unusual, their velocities unexpected, their compositions different enough from typical asteroids to confuse automated classification systems designed for solar system natives. The timeline for these threats could span generations. Unlike the immediate drama of impacts or atmospheric disruption, gravitational perturbations operate on what physicists call secular timescales, changes that accumulate slowly but inexorably over periods measured in decades or centuries. We might not fully understand the consequences of 3I Atlas October 3rd encounter with Mars until the 2040s, 2050s, or beyond, when fragments finally begin threatening Earth in ways that trace back to this single cosmic encounter. This temporal displacement of consequences creates a particularly insidious form of cosmic risk. The politicians and space agency administrators making planetary defense decisions today might not be around to face the consequences when 3I Atlas-derived fragments begin threatening Earth decades in the future. The institutional memory and funding commitments needed to address long-term orbital threats operate on timescales that exceed typical political and bureaucratic attention spans. As we prepare to examine our final and perhaps most disturbing scenario, we must confront the possibility that all of our focus on physical destruction, chemical contamination, and orbital chaos might be missing the point entirely. What if the worst-case outcome of 3I Atlas encounter with Mars isn't any form of planetary catastrophe, but something far more subtle and infinitely more dangerous to human civilization? What if the real disaster unfolds not in space, but in the information systems and decision-making processes that determine how our species responds to cosmic uncertainty? In our final segment, we'll explore how 3I Atlas could weaponize our own psychology against us, creating informational cascades that prove more destructive to human civilization than any physical impact could ever be. Part 6. The Information Weapon. In the age of digital connectivity, information moves faster than light through fiber optic cables and spreads more explosively than any cosmic impact. What we're about to explore represents a category of disaster that no planetary defense system was ever designed to address: the weaponization of uncertainty itself. The most devastating consequence of 3I Atlas encounter with Mars might not be measured in crater diameters or electromagnetic disruptions, but in the collapse of rational discourse about cosmic threats. Consider the perfect storm of conditions that October 3rd presents for informational catastrophe. The encounter occurs during solar conjunction, when our observational capabilities are severely limited. The scientific data requires weeks or months of careful analysis before meaningful conclusions can be drawn. Most critically, the event involves an interstellar object whose behavior has consistently defied our models and expectations. NASA and the European Space Agency have been conspicuously measured in their public communications about 3I Atlas. Official statements acknowledge the unusual nature of the object and confirm plans for observational campaigns, but they stop short of providing the kind of dramatic speculation that captures public imagination. This cautious approach, while scientifically appropriate, creates an information vacuum that alternative narratives rush to fill with increasing desperation. Social media algorithms designed to maximize engagement rather than accuracy naturally amplify the most dramatic and alarming interpretations of incomplete data. By the time official scientific analysis reaches completion, public opinion may be so thoroughly shaped by misinformation that factual corrections become not just ineffective, but actively rejected as evidence of institutional cover-ups. The precedent for astronomical misinformation campaigns offers little comfort. The speed with which speculation can outpace official information when dealing with phenomena that challenge conventional understanding has been demonstrated repeatedly in recent years. Congressional hearings intended to provide transparency instead generate more questions than answers, feeding conspiracy theories rather than resolving them. 3I Atlas presents an even more complex challenge because the object is genuinely anomalous in ways that resist simple explanation. Its massive carbon dioxide emissions, erratic brightness variations, and exotic chemical signatures provide just enough genuine mystery to make even outlandish theories seem plausible to non-expert audiences. The boundary between legitimate scientific uncertainty and baseless speculation becomes increasingly difficult to maintain. The delayed release schedule for scientific data compounds the problem exponentially. James Webb Space Telescope observations conducted throughout the summer remain under analysis by research teams following peer review protocols that prioritize accuracy over speed. Preliminary results might not be publicly available until months after the October 3rd encounter, creating a prolonged period when speculation operates without any factual constraints whatsoever. Meanwhile, amateur astronomers and citizen science groups conduct their own observations with equipment that, while impressive for backyard standards, lacks the sensitivity and calibration of professional observatory instruments. Their measurements, shared instantly across social media platforms, may contain artifacts or misinterpretations that professional astronomers would immediately recognize, but which appear compelling to general audiences hungry for immediate answers. Picture this nightmare timeline unfolding over the coming weeks. 3I Atlas passes Mars on October 3rd, with what appears to be minimal fanfare, producing subtle changes in the planet's electromagnetic environment that require sophisticated analysis to detect and understand. Mars orbiters continue functioning normally, but implement precautionary protocols that temporarily reduce science operations as a safety measure. From a scientific perspective, this represents an interesting but non-catastrophic encounter that provides valuable data about interstellar object interactions with planetary magnetospheres. Surface rovers experience brief communication interruptions as ionospheric conditions fluctuate. Nothing dramatic enough to generate compelling footage for social media, but technically significant enough to require careful study. But from a public information perspective, these mundane technical details could be interpreted as evidence of deliberate suppression. The temporary reduction in Mars imagery transmission creates a blackout period that conspiracy theorists interpret as proof that something terrible has occurred. Technical explanations about ionospheric propagation effects and spacecraft operating procedures sound like bureaucratic doublespeak to audiences primed to expect dramatic revelations. Social media fills with increasingly elaborate theories about what really happened during the 3I Atlas encounter. Computer-generated images purporting to show Mars impact craters circulate faster than official corrections can be issued. Amateur radio operators claim to have intercepted emergency transmissions from Mars orbiters that space agencies refuse to acknowledge. Each debunked theory spawns 3 new ones, creating an information hydra that grows stronger with every attempt to contain it. The psychological dynamics driving such information cascades are well understood by cognitive scientists, but remain poorly addressed by official communication strategies. When people are primed to expect dramatic events, normal scientific caution gets interpreted as evasion. When official explanations involve technical details that require specialized knowledge to understand, they're dismissed as attempts to obscure rather than illuminate. Congressional oversight intended to ensure transparency and accountability could actually amplify misinformation if representatives without scientific training demand answers to questions that can't be answered definitively with available data. Hearings that feature dramatic testimony about potential cosmic threats could generate media coverage that treats speculation as established fact, creating a feedback loop where political pressure forces premature disclosure of preliminary results. The international dimension adds another layer of complexity to information management. Different space agencies operating under different political constraints might release information on schedules that don't align perfectly. These timing differences could be interpreted as evidence of coordination failures or deliberate information manipulation rather than routine operational considerations. Amateur astronomers in countries with different transparency traditions might share observations that contradict or complicate official narratives from Western space agencies. Chinese or Russian space programs operating under different political pressures might characterize the same events in ways that seem inconsistent with NASA or ESA interpretations. The cumulative effect could be a global information environment where multiple contradictory versions of what really happened compete for public attention. But perhaps most insidiously, the information disaster scenario could become self-fulfilling if public pressure forces premature disclosure of preliminary scientific results that later prove incorrect. Space agencies facing congressional inquiries and media scrutiny might feel compelled to release tentative findings that satisfy public demand for immediate answers, but lack the rigorous analysis needed for scientific accuracy. These premature disclosures, when later corrected by more complete analysis, could be interpreted as evidence of incompetence or deliberate deception rather than normal scientific process. The correction cycle, where initial dramatic claims are gradually moderated by more careful study, mirrors exactly the pattern that fuels conspiracy theories about government cover-ups and institutional dishonesty. The long-term consequences for space science could prove severe and lasting. Public trust in space agencies, built up over decades of successful missions and stunning discoveries, could be damaged by information management failures during the 3I Atlas encounter. Future missions might face skeptical audiences who've been conditioned to doubt official explanations of astronomical phenomena. International cooperation in space exploration, already strained by terrestrial political conflicts, could suffer additional damage if different agencies are perceived to be providing contradictory information about the same cosmic events. The collaborative spirit that makes complex space missions possible depends on shared commitment to transparency and scientific integrity. Yet even as we contemplate these informational nightmares, we must prepare for the possibility that October 3rd will pass without providing clear resolution to any of the questions 3I Atlas has raised. What happens when the most significant astronomical event of our generation occurs and leaves us with more mysteries than answers? What happens when the universe refuses to provide the dramatic closure that human psychology demands? The anticlimactic scenario might prove more psychologically devastating than any cosmic catastrophe. Months of speculation about potential disasters, followed by an encounter that produces no obvious drama, could leave the public feeling manipulated and deceived. The absence of spectacle could be interpreted as evidence that the entire threat was manufactured by institutions seeking increased funding or political relevance. This psychological whiplash could prove more damaging to scientific credibility than any technical failure. A public that feels betrayed by what they perceive as false alarms might become resistant to future warnings about genuine cosmic threats. The boy who cried wolf dynamic could leave us vulnerable to real dangers that arrive without the dramatic build-up that captures media attention. Educational institutions find themselves caught between competing pressures to maintain scientific accuracy while acknowledging genuine uncertainty. Students who have followed 3I Atlas as a real-time case study might lose interest if the encounter fails to produce obvious drama, missing the subtle but important scientific discoveries that careful analysis will eventually reveal. The speed with which public attention shifts from one crisis to another could leave important lessons unlearned. 3. I-Atlas represents our first well-documented encounter with a chemically exotic interstellar visitor, providing data that will inform our understanding of cosmic threats for decades to come. But if media attention moves on before that analysis is complete, the educational value of this encounter could be largely wasted. Perhaps most troubling is how this informational chaos could affect our response to future cosmic encounters. If the 3I Atlas experience leaves us with damaged trust between scientific institutions and public audiences, weakened international cooperation in space monitoring, and degraded ability to distinguish between genuine threats and manufactured crises, we might find ourselves poorly prepared for the next interstellar visitor that follows in its ancient wake. The universe operates on timescales that dwarf human attention spans and political cycles. The next genuine cosmic threat might arrive during a period when our information systems are still recovering from the self-inflicted wounds of the 3I Atlas encounter. The most devastating legacy of this interstellar visitor might not be any physical damage it causes, but the institutional and psychological damage we cause to ourselves while trying to understand what it means. As October 3rd approaches and our observational window narrows, we face a test that transcends astronomy and planetary science. This is a test of our civilization's capacity to maintain rational discourse under conditions of uncertainty, to distinguish between genuine scientific mystery and manufactured crisis, and to preserve the institutional trust that makes complex technological societies possible. The outcome of this test will determine not just how we respond to 3I Atlas, but how prepared we are for the next cosmic challenge that awaits us among the stars. Whether we pass or fail might not become apparent until long after this particular interstellar visitor has continued its ancient journey back to the cosmic deep, carrying with it whatever lessons we prove capable of learning about our place in a universe far stranger and more active than we ever dared imagine. Part 7. The Cascading Failure. The nightmare scenario that keeps space agency directors awake at night isn't necessarily the dramatic collision or electromagnetic storm we've been exploring. It's something far more insidious and potentially irreversible. The possibility that 3I Atlas could trigger a cascade of failures that transforms Mars from humanity's next home into our greatest warning about the dangers lurking in the cosmic wilderness. Picture this unfolding over the weeks following October 3rd. The initial encounter appears routine to casual observers. 3. I-Atlas sweeps past Mars at its predicted distance. Our robotic assets continue their observations, and preliminary reports suggest nothing catastrophic has occurred. But beneath this veneer of normalcy, subtle changes begin manifesting in ways that won't become apparent until it's far too late to respond effectively. The first signs emerge in the atmospheric data. Mars's thin envelope of gases, already precarious and vulnerable, begins showing chemical signatures that don't match any historical records. The exotic organic compounds we discussed earlier aren't just contaminating surface soil. They're interacting with atmospheric chemistry in ways that create self-sustaining reaction chains. What begins as trace contamination gradually amplifies through feedback loops that our models never anticipated. These aren't the dramatic atmospheric changes that would capture media attention. Instead, they're subtle shifts in molecular ratios, minor alterations in photochemical processes, and gradual modifications to the planet's energy balance. The kind of changes that require months of careful analysis to detect. and years of observation to fully understand. By the time we recognize what's happening, the cascade has already progressed beyond any possibility of intervention. The electromagnetic effects compound these chemical changes in ways that create synergistic destruction. Mars's already weak magnetic field becomes further disrupted by the lingering presence of charged particles from 3I Atlas. This creates a feedback loop where atmospheric chemistry changes alter the planet's electrical properties, which in turn affect how solar wind interacts with the upper atmosphere, which then drives additional chemical modifications. Our spacecraft, designed to operate in Mars' predictable electromagnetic environment, begin experiencing cascading failures that mirror the planetary chaos below. Communication systems that worked reliably for years start showing intermittent problems. Star trackers lose their reference points as the planet's magnetic field fluctuations create spurious signals. Solar panels degrade more rapidly than expected as the altered atmospheric chemistry changes how particles interact with photovoltaic surfaces. The Mars Reconnaissance Orbiter, humanity's primary eye in Martian orbit, begins showing signs of premature aging that accelerate with each passing week. Components that were rated for decades of operation start failing after months of exposure to the chemically and electromagnetically altered environment. The spacecraft's sophisticated instruments, calibrated for Mars' historical conditions, produce increasingly unreliable data as the planet they're studying transforms beneath them. MAVEN, specifically designed to understand Mars's atmospheric evolution, finds itself documenting changes that occur faster than its mission planners ever imagined possible. The spacecraft's particle detectors, built to measure gentle solar wind interactions, become overwhelmed by the chaotic electromagnetic environment that 3I Atlas has left behind. Instead of studying Mars' ancient atmospheric loss, MAVEN becomes an accidental witness to rapid atmospheric transformation occurring in real time. The surface rovers face their own escalating challenges as the cascade effects reach ground level. Dust storms, already a persistent hazard for solar-powered equipment, become more frequent and more intense as atmospheric chemistry changes alter temperature gradients and pressure differentials. The fine Martian dust that coats everything begins showing different electrical properties, creating static buildup that interferes with delicate electronic systems. Perseverance and Curiosity, engineering marvels designed to operate for years in the Martian environment, start experiencing accelerated wear on their mechanical systems. The altered atmospheric chemistry affects lubricants and seals in ways that weren't anticipated during Earth-based testing. Wheel degradation, always a concern for Mars rovers, accelerates as the changed surface chemistry creates more abrasive interactions. Martian soil between metal components But the most devastating aspect of this cascade failure isn't the loss of individual systems. It's the collapse of our observational network just when we need it most to understand what's happening. As spacecraft fail and rovers succumb to environmental changes, we lose our ability to monitor and analyze the ongoing transformation of Mars. We become blind to the very processes that are reshaping the planet's future habitability. The timeline for recognizing this cascade extends far beyond typical mission planning horizons. Unlike the immediate drama of impacts or electromagnetic storms, systemic failure operates on timescales measured in years rather than days. Each individual component failure might seem routine, the kind of gradual degradation expected from aging spacecraft operating in harsh environments. Only when viewed collectively does the pattern of cascading destruction become apparent. Ground controllers at mission operations centers find themselves fighting an increasingly desperate battle to maintain contact with their robotic charges. Software patches and operational workarounds that bought time for aging spacecraft systems become less effective as the fundamental environment those systems were designed for continues changing. Standard troubleshooting procedures prove inadequate for problems caused by conditions that didn't exist when the spacecraft were built. The psychological impact on Mars exploration teams becomes severe as they watch decades of careful planning and billions of dollars in sophisticated hardware succumb to forces they can't control or fully understand. Engineers who dedicated their careers to Mars exploration find themselves managing the systematic failure of missions they helped design. The institutional knowledge and operational expertise built up over decades of Mars exploration begins fragmenting as missions end prematurely and teams disperse. International cooperation in Mars exploration, already challenged by budget constraints and political pressures, faces additional strain as different space agencies lose their primary assets at different rates. The European Space Agency's orbiters might succumb to cascade effects on different timelines than NASA's systems, creating information gaps and coordination challenges that complicate joint scientific analysis. The loss of our Mars observational network has implications that extend far beyond scientific disappointment. Mars serves as our laboratory for understanding planetary atmospheres, climate evolution, and the potential for life beyond Earth. Without continuous monitoring capabilities, we lose our ability to study these fundamental questions just when the planet is undergoing its most dramatic changes in millions of years. Future Mars missions, already facing extended development timelines and escalating costs, confront the additional challenge of operating in an environment that no longer matches our historical understanding. Landing site selection, trajectory planning, and system design all require revision based on incomplete knowledge of how 3I Atlas has altered Martian conditions. Mission success rates could plummet as spacecraft encounter environmental conditions their designers never anticipated. The contamination effects spread beyond Mars itself through mechanisms we're only beginning to understand. Debris from 3I Atlas, carrying exotic organic compounds and unusual chemistry, doesn't remain confined to the immediate vicinity of the red planet. Some material gets ejected from Mars' gravitational influence through atmospheric interactions and electromagnetic effects, creating a dispersed cloud of contamination that could affect other objects in the inner solar system. This dispersed contamination follows orbital mechanics that could eventually bring exotic materials into Earth's vicinity, not in concentrations sufficient to cause immediate biological effects, but potentially enough to complicate our understanding of natural processes in our own environment. Future studies of interplanetary dust, atmospheric chemistry, and even meteorite compositions might be affected by trace contamination originating from the 3I Atlas encounter. The asteroid belt, that vast collection of rocky debris between Mars and Jupiter, becomes another potential repository for 3I Atlas contamination. Objects that interact gravitationally with Mars during the weeks and months following the encounter could carry traces of exotic chemistry to regions of the solar system where future mining operations and scientific missions might encounter them decades or centuries from now. The cascading failure scenario forces us to confront uncomfortable truths about our technological civilization's relationship with cosmic forces beyond our control. We've built our Mars exploration programs on the assumption that planetary environments remain relatively stable over the timescales relevant to human missions. 3I Atlas demonstrates how quickly that assumption can prove catastrophically wrong. Our spacecraft, despite their sophisticated engineering and redundant systems, remain fundamentally vulnerable to environmental changes that exceed their design parameters. The same precision that makes them capable of extraordinary scientific discoveries also makes them fragile when operating conditions drift outside anticipated ranges. We've created technological marvels that can function flawlessly for decades under expected conditions, but which become expensive debris when the environment changes in unexpected ways. The institutional memory loss that accompanies premature mission failures creates long-term consequences that extend beyond immediate scientific setbacks. Each spacecraft represents not just hardware, but accumulated operational knowledge, flight experience, and understanding of how systems behave in the Martian environment. When missions end abruptly due to environmental changes rather than planned obsolescence, that institutional knowledge disappears without being fully transferred to future projects. Educational institutions that have built curricula around active Mars missions find themselves teaching planetary science with outdated examples and incomplete data sets. Students preparing for careers in space exploration learn about Mars exploration during a period when our capabilities are contracting rather than expanding. The inspirational value of ongoing missions, crucial for maintaining public support and attracting talent to space sciences, diminishes as robotic explorers succumb to environmental challenges. The economic implications cascade through aerospace industries that have invested heavily in Mars exploration technologies. Companies that developed specialized systems for Martian operations face reduced demand as mission planners become more conservative about deploying expensive assets in an increasingly unpredictable environment. The commercial space economy, already challenged by long development timelines and high technical risks, faces additional uncertainty about the reliability of planetary environment assumptions. Insurance markets, already reluctant to provide coverage for space missions, become even more conservative as the 3I Atlas encounter demonstrates how quickly environmental assumptions can prove wrong. Premium costs for Mars missions increase dramatically as underwriters struggle to assess risks in an environment that's changing faster than historical data can characterize. Some categories of Mars exploration become effectively uninsurable, forcing space agencies to accept higher levels of self-assumed risk. Yet even as we contemplate this cascade of technological and institutional failures, we must acknowledge that the most profound consequence of 3I Atlas might not be what it does to Mars, but what it reveals about humanity's preparedness for cosmic citizenship. The encounter serves as an unintentional stress test of our ability to respond rationally to phenomena that challenge our assumptions about how the universe operates. In our final examination, we'll explore how 3I Atlas might function not as a destroyer of worlds, but as a cosmic teacher delivering lessons about humility, preparedness, and the true nature of our relationship with forces that operate on scales vastly exceeding human control. The question isn't just whether Mars survives its encounter with this interstellar visitor, but whether human civilization proves capable of learning from cosmic events that dwarf our earthly experience. Part 8. The Cosmic Mirror. As we stand on the threshold of October 3rd, watching 3I Atlas complete its inexorable approach toward Mars, we must confront a possibility that transcends all the physical scenarios we've explored. What if this interstellar wanderer serves not as an agent of destruction, but as a cosmic mirror reflecting our civilization's deepest vulnerabilities and most urgent need for growth? What if the worst-case scenario isn't what 3I Atlas does to Mars, but what it reveals about humanity's readiness to exist in a universe far more active and unpredictable than we ever imagined? The encounter has already exposed fractures in our information systems that could prove more dangerous than any electromagnetic storm. We've witnessed how quickly speculation can overwhelm evidence when dealing with phenomena that challenge our understanding. Social media algorithms designed to maximize engagement have amplified dramatic interpretations at the expense of measured analysis. The same communication networks that enable global scientific collaboration have become vectors for misinformation that spreads faster than factual corrections can contain it. Congressional hearings intended to provide transparency have instead generated more heat than light, with representatives lacking scientific expertise demanding answers to questions that can't be resolved with available data. The careful, methodical approach that characterizes good science has been reframed as institutional secrecy by audiences conditioned to expect immediate answers to complex questions. We're learning that our democratic institutions, designed for terrestrial challenges, may be poorly adapted for managing cosmic uncertainties. International cooperation in space exploration, already strained by terrestrial political conflicts, faces additional pressure as different agencies provide information on different timelines according to their own institutional constraints and political considerations. The timing differences between NASA and ESA announcements, routine in normal circumstances, become fodder for conspiracy theories about coordinated information suppression. We're discovering that the collaborative spirit essential for understanding cosmic phenomena remains vulnerable to the same political divisions that complicate terrestrial challenges. The amateur astronomy community, typically a source of valuable observations and public engagement, has become fragmented between those following rigorous scientific protocols and those promoting increasingly exotic theories about 3I Atlas unusual behavior. The democratization of astronomical observation, generally beneficial for science education and public participation, has created new challenges for distinguishing reliable observations from artifacts and misinterpretations. Educational institutions find themselves caught between competing pressures to acknowledge genuine scientific uncertainty while avoiding the kind of sensational speculation that undermines public understanding of how science actually works. Teachers and professors who have used 3I Atlas as a real-time case study in planetary science must navigate the delicate balance between inspiring student interest and maintaining scientific integrity. The pedagogical value of studying an active cosmic mystery becomes complicated when that mystery generates more confusion than clarity. But perhaps most revealing is how the 3I Atlas encounter has highlighted the temporal mismatch between cosmic events and human decision-making processes. The universe operates on timescales that dwarf political cycles, budget allocations, and institutional planning horizons. The most significant consequences of cosmic encounters often don't become apparent until years or decades after the initial event, requiring sustained observation and analysis commitments that exceed typical human attention spans. Our space agencies, despite their technical sophistication, remain embedded within political and economic systems that prioritize short-term results over long-term understanding. The kind of patient, systematic observation required to fully comprehend 3I Atlas' impact on Mars might extend beyond the career spans of the administrators who authorize the studies. This creates institutional challenges for maintaining continuity in cosmic threat assessment and response planning. The insurance industry's response to 3I Atlas has been particularly illuminating. Underwriters accustomed to calculating risks based on historical data find themselves confronting phenomena with no precedent in human experience. How do you price insurance for Mars missions when interstellar visitors can alter planetary environments in unpredictable ways? How do you assess the reliability of space systems designed for conditions that might not persist throughout their operational lifetimes? Private space companies that have invested billions in Mars exploration technologies face fundamental questions about the stability of their business models. If interstellar objects can regularly disrupt planetary environments, the economic assumptions underlying commercial Mars development require complete reconsideration. The same entrepreneurial spirit that has revolutionized access to space might need to adapt to cosmic realities that make long-term planning far more challenging than terrestrial ventures. The psychological impact on space exploration communities has been profound and unexpected. Engineers and scientists who dedicated their careers to Mars exploration find themselves questioning assumptions they never thought to examine. The red planet, which seemed like a predictable destination for human expansion, has been revealed as potentially far more dynamic and hazardous than our models suggested. Career planning in space sciences must now account for the possibility that entire research programs could be disrupted by cosmic events with little warning. Yet these revelations about our limitations might represent 3I Atlas' most valuable contribution to human civilization. By exposing the fragility of our assumptions and the inadequacy of our current frameworks for cosmic risk assessment, this interstellar visitor forces us to mature as a spacefaring species. The lessons we learn from confronting our own ignorance could prove more valuable than any scientific data we gather about the comet itself. the encounter demonstrates the urgent need for more robust international frameworks for coordinating responses to cosmic phenomena. The current patchwork of bilateral agreements and voluntary cooperation protocols proves inadequate when dealing with events that could affect multiple planets and spacecraft simultaneously. We need institutions specifically designed to manage cosmic uncertainties, rather than trying to adapt terrestrial frameworks to challenges they were never intended to address. Our detection and monitoring systems, impressive as they've become, remain primarily focused on threats originating within our solar system. The 3I Atlas encounter reveals how little we understand about the population of interstellar objects that regularly pass through our cosmic neighborhood. Future surveys need to be redesigned with the understanding that the space between stars isn't empty, but populated with wanderers that could dramatically affect planetary environments with little warning. The technological implications extend beyond planetary defense to encompass fundamental questions about how we design systems intended to operate in cosmic environments. Our spacecraft, despite their sophisticated engineering, remain essentially designed for the relatively predictable conditions that prevail within our solar system. Interstellar visitors introduce variables that our current engineering approaches struggle to accommodate. Future space systems might need to be designed with far greater adaptability and resilience than current approaches provide. Instead of optimizing for known conditions, we might need to prioritize flexibility and robustness that allows systems to continue functioning even when environmental assumptions prove wrong. This represents a fundamental shift in space system design philosophy that could affect everything from communication satellites to Mars rovers. The educational implications are equally profound. Students currently learning astronomy and planetary science are studying during a period when our understanding of cosmic phenomena is undergoing rapid revision. The textbooks they read describe a universe that seems more orderly and predictable than the reality 3I Atlas has revealed. Future curricula need to better prepare students for careers in fields where fundamental assumptions might be overturned by observations that haven't been made yet. Public science communication faces similar challenges. The traditional approach of presenting scientific knowledge as established fact becomes problematic when dealing with phenomena that challenge established frameworks. Science communicators need new approaches that can convey genuine uncertainty without undermining public confidence in scientific methods. The balance between acknowledging ignorance and maintaining credibility becomes particularly delicate when dealing with cosmic threats that could affect human welfare. The 3I Atlas encounter might ultimately be remembered not for any specific effects it has on Mars, but for the way it forced human civilization to confront our cosmic immaturity. We've spent centuries developing sophisticated technologies and institutions, but always within the comfortable assumption that space was essentially static between major solar events and asteroid impacts. The realization that interstellar visitors could regularly disrupt this assumed stability requires fundamental reconsideration of how we approach space exploration and planetary security. The mirror that 3I Atlas holds up to human civilization reflects both our remarkable achievements and our dangerous limitations. We've built spacecraft that can operate for years on distant worlds and telescopes that can analyze the chemical composition of objects billions of kilometers away. But we've also created information systems that amplify speculation faster than truth and decision-making processes that struggle with uncertainties extending beyond electoral cycles. Perhaps the most important lesson emerging from this encounter is the recognition that cosmic citizenship requires different approaches to knowledge, cooperation, and risk management than terrestrial challenges demand. The universe operates according to principles that don't respect national boundaries, political ideologies, or human timescales. Our survival and prosperity as a spacefaring species depends on developing institutions and technologies that can function effectively within cosmic, rather than merely terrestrial constraints. As October 3rd approaches and our observational capabilities focus on the Mars encounter, We're participating in more than just an astronomical event. We're undergoing a species-wide education in cosmic realities that will shape how future generations approach the challenges and opportunities of living in a universe far more dynamic than we previously understood. Whether we prove capable of learning these lessons might determine not just our response to 3i Atlas, but our readiness for the next cosmic teacher that follows in its ancient wake. The worst-case scenario for 3i Atlas might not be planetary destruction or technological failure, but the possibility that we'll waste this unprecedented opportunity to grow as a cosmic civilization. The universe has delivered a masterclass in humility and preparedness directly to our solar system. Whether we graduate or repeat the course depends entirely on how well we absorb the lessons this interstellar visitor has come so far to teach us. Part 9. The Silent Countdown. The calendar pages turn with mechanical precision as October 3rd draws near, each passing day bringing us closer to a cosmic rendezvous that could redefine everything we thought we knew about interstellar visitors. But perhaps the most disturbing aspect of our current situation isn't the approaching encounter itself. It's the eerie calm that has settled over official channels in the final weeks before contact. NASA's daily briefings have taken on an almost ritualistic quality, delivering technical updates about 3i Atlas trajectory with the kind of measured precision that suggests careful script preparation. The European Space Agency's status reports follow remarkably similar patterns, emphasizing routine observational protocols while avoiding speculation about potential outcomes. This coordinated restraint, while professionally appropriate, creates an information environment that feels increasingly disconnected from the magnitude of what we're actually witnessing. Behind this facade of institutional calm, however, the astronomical community is experiencing something approaching controlled panic. Private communications between researchers reveal growing concerns about observational anomalies that don't appear in public reports. 3i Atlas continues generating brightness flares that follow no predictable pattern, creating spectroscopic signatures that resist conventional interpretation. The object's massive carbon dioxide emissions have intensified rather than diminished as it approaches Mars, defying every model of normal comet behavior. Ground-based telescopes worldwide are capturing data that individual research teams analyze in isolation, their findings filtered through institutional review processes that prioritize caution over rapid disclosure. Amateur astronomers with sophisticated equipment are documenting variations in 3i Atlas appearance that suggest ongoing structural changes within the object itself. These observations, shared through informal networks and social media platforms, paint a picture of an interstellar visitor that becomes more mysterious rather than more comprehensible as we study it more closely. The timing constraints imposed by solar conjunction add urgency to every measurement and calculation. Within days of October 3rd, our ability to observe the Mars encounter will degrade significantly as the Sun's position makes direct observation increasingly difficult. The most critical phase of 3i Atlas passage will occur precisely when our monitoring capabilities are most severely compromised, creating an observational blindness that astronomers find deeply unsettling. Mars itself presents a target that seems almost designed to maximize the potential consequences of any anomalous behavior from 3i Atlas. The planet's thin atmosphere provides minimal protection against high-velocity impacts or charged particle bombardment. Its weak magnetic field offers little shielding against electromagnetic effects that could disrupt both planetary systems and the sophisticated spacecraft currently orbiting the red planet. In cosmic terms, Mars stands essentially naked before whatever forces this interstellar wanderer might unleash. The Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter represent billions of dollars in sophisticated technology and decades of accumulated operational experience. These robotic explorers have functioned as our eyes and ears at Mars, documenting everything from ancient riverbeds to seasonal atmospheric changes. But they were designed for a Mars that operates according to predictable physical principles, not for a world that might be about to encounter forces from beyond our solar system. Recent orbital adjustments to several Mars spacecraft suggest that mission controllers are taking precautionary measures that haven't been publicly announced. Subtle changes in communication schedules and data transmission patterns indicate preparation for potential disruptions that official statements don't explicitly acknowledge. The spacecraft are being positioned and configured as if their operators expect conditions around Mars to become significantly more challenging in the near future. Surface operations present even greater vulnerabilities. The Perseverance and Curiosity rovers, engineering marvels that have exceeded their planned mission lifetimes, continue their exploration of Martian geology with the methodical precision that has characterized robotic exploration for decades. But their solar panels, communication systems, and delicate scientific instruments remain vulnerable to environmental changes that their designers never anticipated when the missions were planned years ago. The dust storm implications alone create scenarios that keep mission planners awake at night. Mars is notorious for global dust storms that can engulf the entire planet for months at a time, blocking sunlight and disrupting communication with orbiting spacecraft. If 3I Atlas encounter triggers enhanced atmospheric activity through electromagnetic effects or debris interactions, the resulting dust storms could persist far longer than normal seasonal patterns would suggest. Worse still, the chemical composition of dust storms triggered by interstellar contamination might differ significantly from normal Martian dust events. Exotic organic compounds introduced by 3I Atlas could alter the electrical properties of atmospheric particles, creating static buildup and electromagnetic interference that conventional spacecraft systems weren't designed to handle. Even routine operations like solar panel deployment and antenna positioning could become problematic if atmospheric particles exhibit unusual electrical behavior. The communication challenges extend beyond simple dust interference to encompass fundamental questions about how electromagnetic signals propagate through a planetary environment that might be undergoing rapid chemical and electrical changes. Radio frequencies that work reliably under normal Martian conditions could become unusable if 3I Atlas introduces ionospheric disturbances or charged particle populations that interfere with signal transmission. Mission control centers at JPL, ESA, and other space agencies have been conducting simulation exercises that test their responses to various communication failure scenarios. These exercises, while routine for normal operations, have taken on increased urgency as October 3rd approaches. The possibility that multiple Mars assets could experience simultaneous communication problems during the 3I Atlas encounter has forced mission planners to develop contingency protocols for operating with severely degraded information about spacecraft status and planetary conditions. The psychological pressure on mission teams has intensified as they prepare for an event that could fundamentally alter the environment their spacecraft were designed to explore. Engineers who have spent years learning the intricacies of Mars operations find themselves contemplating scenarios where their accumulated expertise might become obsolete overnight. The institutional knowledge built up through decades of successful Mars missions could prove inadequate for managing operations in a post-3I Atlas environment. International coordination efforts have intensified behind the scenes, as space agencies recognize that the 3rd of October encounter might require unprecedented levels of cooperation. Data sharing agreements that normally take months to negotiate have been expedited to ensure that information about 3I Atlas effects can be distributed rapidly among all Mars mission operators. The realization that this interstellar visitor could affect multiple spacecraft simultaneously has created new urgency around collaborative response planning. But perhaps most unsettling is what we don't know about institutional preparations that remain classified or compartmentalized within government agencies. Planetary defense organizations designed to address asteroid and comet threats have been conspicuously quiet about their assessment of 3I Atlas, suggesting either that they consider the object genuinely harmless, or that their concerns exceed what they're comfortable discussing in public forums. The silence from military space surveillance systems, which routinely track objects much smaller than 3I Atlas, raises questions about whether government agencies have detected characteristics of this interstellar visitor that haven't been shared with civilian researchers. The dual-use nature of space surveillance technology means that the most sensitive observations of 3I Atlas might be classified under national security protocols that prevent their inclusion in academic research. Commercial space companies with Mars-related investments have been equally circumspect about their preparations for potential disruptions to the Martian operating environment. SpaceX, Blue Origin, and other firms developing Mars transportation and habitat systems have avoided public speculation about how 3I Atlas might affect their long-term business plans. This institutional silence could reflect either confidence that the encounter will prove benign or concerns about market reactions to acknowledged uncertainties about Mars exploration timelines. The insurance industry's response provides another indicator of institutional concern levels that exceed public statements. Premium adjustments for Mars mission coverage suggest that underwriters are pricing in higher risks than official probability assessments would seem to justify. The actuarial calculations that determine space mission insurance costs apparently incorporate factors that don't appear in NASA or ESA public risk analyses. As the final days before October 3rd tick away, the contrast between official reassurance and behind-the-scenes preparation becomes increasingly apparent. The measured tone of public briefings exists alongside frantic activity in mission control centers, research institutions, and government agencies that suggests far greater concern about potential 3I Atlas effects than official statements acknowledge. This disconnect between public communication and private preparation creates an information environment that breeds speculation and conspiracy theories. When institutional behavior suggests higher concern levels than public statements acknowledge, audiences naturally begin questioning whether they're receiving complete and accurate information about cosmic events that could affect human welfare and scientific progress. The approaching solar conjunction that will limit our observational capabilities during the most critical phase of the encounter adds another layer of uncertainty to an already complex situation. Just when we need maximum visibility into what's happening at Mars, astronomical geometry will blind us to the very phenomena we most need to understand. It's as if the universe has conspired to hide the most important moments of this cosmic encounter from human observation. The countdown to October 3rd proceeds with the inevitability of orbital mechanics. Each passing hour bringing 3I Atlas closer to its appointment with Mars and humanity, closer to discovering whether our worst fears or most optimistic projections prove accurate. The silence from official channels becomes more ominous as the encounter approaches, suggesting either careful management of public expectations or genuine uncertainty about what this interstellar wanderer might unleash upon reaching its closest approach to the red planet. In just days, we'll learn whether months of speculation about cosmic catastrophe were justified or whether 3I Atlas will pass Mars as quietly as conventional models predict. But the institutional behavior surrounding this encounter suggests that whatever happens on October 3rd, our understanding of interstellar visitors and their potential impact on planetary environments will never be quite the same. The silence isn't just about managing public anxiety. It's about preparing for discoveries that could fundamentally alter our approach to cosmic threats and planetary defense for generations to come. The final countdown has begun, and with it, humanity's first real test of how well we can respond to cosmic uncertainties that transcend our earthly experience and challenge our most fundamental assumptions about the predictability of space itself. Part 10. The event horizon. We've reached the point where theoretical analysis must yield to observational reality. October 3rd, 2025 stands before us like an event horizon in space-time, beyond which our ability to predict outcomes dissolves into pure uncertainty. Every model we've constructed, every scenario we've explored, every worst-case projection we've contemplated now awaits validation or refutation by the immutable laws of physics playing out across 30 million kilometers of Martian space. The final preparations unfolding across the global astronomical community carry an undercurrent of tension that no amount of professional composure can entirely conceal. Mission control centers that normally operate with the calm efficiency of well-oiled machines now buzz with the kind of barely controlled energy typically reserved for landing sequences or critical orbital maneuvers. The difference is that this time, we're not controlling the variables. We're simply witnesses to whatever 3i Atlas decides to unleash. Deep Space Network facilities in California, Spain, and Australia have synchronized their operations with military precision, creating a global listening post that will strain to maintain contact with our Martian assets through whatever chaos might emerge. The massive dish antennas, normally pointed toward routine communication targets, now track with the focused intensity of hunters following dangerous prey. Every minute of contact time has been scheduled and rescheduled, optimized for maximum data collection during the brief windows when both geometry and solar interference allow clear signals. The James Webb Space Telescope, humanity's most sophisticated eye on the cosmos, has been oriented toward the Mars 3i Atlas encounter zone with the kind of priority typically reserved for the most significant astronomical events of our generation. Its infrared sensors, capable of detecting heat signatures across interplanetary distances, stand ready to document whatever thermal anomalies might emerge from the interaction between interstellar chemistry and planetary atmospheres. The telescope's scheduling committee has cleared all routine observations for the critical 72-hour window, acknowledging that we might be witnessing phenomena that won't recur within human lifetimes. Amateur astronomers worldwide have coordinated their own observation campaigns with enthusiasm that borders on obsession. Backyard telescopes from suburban driveways to remote dark sky locations have been aligned and calibrated for the October 3rd event, creating a distributed observation network that spans continents and time zones. Online forums dedicated to 3i Atlas tracking have become repositories for real-time data sharing, with observers posting images and measurements within minutes of collection. But it's the observations we won't be able to make that create the most anxiety among professional astronomers. Solar conjunction doesn't just limit our view of Mars during the encounter. It creates a communications blackout that could hide the most significant moments of the event behind a wall of solar interference. The cruel irony isn't lost on anyone involved in the observation campaigns. Just when 3i Atlas reaches its moment of closest approach, just when any dramatic effects would be most apparent, our ability to witness them will be severely compromised. Ground-based radar installations have been reconfigured to attempt active sensing of the 3i Atlas debris field, bouncing signals off whatever material the comet might be shedding as it approaches Mars. The returning echoes, analyzed through sophisticated signal processing algorithms, could provide crucial information about the size distribution and velocity patterns of particles that might pose impact threats. But radar has limitations that become critical when dealing with objects traveling at interstellar velocities through the electromagnetic chaos of solar conjunction. The European Space Agency's Mission Control Center in Darmstadt has taken on the atmosphere of a war room, with multiple screens displaying real-time telemetry from Mars Express, the Trace Gas Orbiter, and ground-based tracking stations. Flight controllers, who normally manage routine orbital adjustments and scientific observations, now monitor their spacecraft with the intensity of cardiac surgeons watching vital signs during complex operations. Every anomaly in spacecraft performance, no matter how minor, gets flagged for immediate analysis. NASA's Jet Propulsion Laboratory presents a similar scene of controlled urgency. The Mars Reconnaissance Orbiter and MAVEN mission teams have established continuous monitoring protocols that exceed normal operational requirements by orders of magnitude. Engineers who typically work standard shifts have volunteered for extended duty periods, recognizing that the October 3rd encounter might generate spacecraft emergencies that require immediate response despite communication delays measured in minutes. The psychological pressure on mission teams has reached levels that institutional psychologists normally associate with human spaceflight operations rather than robotic missions. The difference is that astronauts can make real-time decisions to protect themselves from unexpected hazards. Our Mars spacecraft operate under the control of ground-based teams who might not learn about critical situations until the crucial moments for response have already passed. The helplessness of managing robotic assets across interplanetary distances becomes particularly acute when those assets face threats that their designers never anticipated. Surface operations teams managing the Perseverance and Curiosity rovers have implemented modified communication schedules designed to maximize data collection in case normal operations become impossible after October 3rd. Both rovers have been directed to secure positions that offer maximum protection from potential debris impacts or electromagnetic interference. Their solar panels have been oriented for optimal charging efficiency, and their scientific instruments have been calibrated for observations that might need to continue without Earth guidance for extended periods. The contingency planning extends beyond individual spacecraft to encompass system-wide responses to various failure scenarios. If multiple Mars assets lose communication simultaneously, ground controllers need predetermined protocols for attempting recovery operations. If electromagnetic interference prevents normal command uplink, alternative communication methods must be tested and ready for implementation. If debris impacts damage solar panels or communication antennas, power management and data prioritization algorithms must function autonomously. But perhaps the most sobering aspect of these preparations is how they acknowledge the limits of human technological capability when confronted with cosmic forces operating on scales that dwarf our engineering experience. We can build spacecraft that function flawlessly for years in the Martian environment, but we cannot shield them from interstellar visitors that introduce variables beyond our current understanding. We can design communication systems that work reliably across interplanetary distances, but we cannot guarantee they'll function when planetary environments undergo rapid changes triggered by alien chemistry. The insurance implications have created their own category of institutional stress. Lloyd's of London and other major space insurers have been quietly reassessing their exposure to Mars mission losses, calculating potential payouts if multiple spacecraft succumb to 3I Atlas effects. The actuarial mathematics of space insurance become meaningless when dealing with events that have no historical precedent and no reliable probability distributions. Underwriters find themselves pricing policies for risks that exist in the realm of theoretical physics rather than empirical data. Commercial space companies with Mars-related investments have been conducting their own risk assessments behind closed doors. SpaceX's Starship development program, designed specifically for Mars cargo delivery, faces questions about operating in an environment that might be fundamentally altered by interstellar contamination. Blue Origin's lunar and Mars habitat technologies require assumptions about planetary conditions that could prove obsolete if 3I Atlas introduces unexpected variables to Martian environmental systems. The broader implications for human Mars exploration timelines have forced space agencies to consider scenarios they hoped never to confront. If October 3rd produces significant disruption to the Martian environment, planned human missions scheduled for the 2030s might require complete redesign based on altered planetary conditions. Life support systems designed for current Martian atmosphere might prove inadequate if 3I Atlas alters atmospheric chemistry. Landing systems calibrated for known atmospheric density profiles might fail if dust storms or chemical changes affect aerodynamic performance. International coordination efforts have intensified as space agencies recognize that 3I Atlas effects could transcend national boundaries and institutional jurisdictions. Data sharing protocols that normally take months to negotiate have been expedited to ensure rapid information distribution among all Mars mission operators. The recognition that this interstellar visitor could affect multiple countries' space assets simultaneously has created unprecedented urgency around collaborative response planning. The educational implications extend beyond immediate mission concerns to encompass fundamental questions about how we prepare future generations of space scientists and engineers for careers in fields where basic assumptions might be overturned by cosmic events. Students currently studying planetary science are witnessing real-time revision of textbook knowledge about interstellar objects and their potential effects on planetary systems. The October 3rd encounter will likely become a case study that influences space science education for decades to come. Media organizations worldwide have positioned correspondents and technical teams to provide comprehensive coverage of whatever unfolds on October 3rd. But unlike typical space events, where dramatic visuals and clear outcomes create compelling narratives, the 3I Atlas encounter might produce subtle effects that require expert interpretation to understand. Science journalists face the challenge of explaining complex atmospheric chemistry and electromagnetic phenomena to general audiences who expect immediate, definitive answers about whether catastrophe has occurred. Social media platforms have prepared for potential misinformation campaigns that could exploit public anxiety about cosmic threats. Content moderation systems designed to handle terrestrial news events must adapt to cosmic phenomena, where the line between legitimate scientific uncertainty and unfounded speculation becomes increasingly difficult to maintain. The democratization of information that usually benefits science communication could become problematic if incomplete data gets misinterpreted and amplified faster than expert analysis can provide context. As the final hours before October 3rd tick away, the astronomical community finds itself in the unique position of conducting what might be humanity's most important observational campaign under conditions of unprecedented uncertainty. We're using our most sophisticated instruments to study phenomena we don't fully understand, preparing for outcomes we can't reliably predict, and attempting to manage risks we've never encountered before. The event horizon approaches with mathematical precision, carrying with it the promise of answers to questions we've been asking for months and the threat of new questions we haven't yet learned to ask. In less than 48 hours, 3I Atlas will reach its closest approach to Mars, and humanity will discover whether our worst fears about interstellar visitors were justified paranoia or inadequate preparation for cosmic realities that exceed our current understanding. Whatever happens on October 3rd will be recorded not just in scientific journals and mission reports, but in the collective memory of a species learning to navigate cosmic uncertainties that transcend terrestrial experience. The silence before the storm has become almost unbearable, filled with the weight of possibilities that range from cosmic anticlimax to planetary catastrophe. Soon, that silence will be broken by data, by observations, by reality itself imposing its verdict on months of speculation and years of assumptions about our safety in a universe that might be far more dangerous than we ever dared imagine. The countdown continues, indifferent to human anxiety and institutional preparation, following orbital mechanics that care nothing for our readiness or our fears. October 3rd approaches like a cosmic judge, prepared to deliver a verdict on humanity's understanding of interstellar visitors and our preparedness for membership in a galaxy that might be far more active and threatening than our brief technological civilization has yet realized. Part 11. The Moment of Truth. October 3rd, 2025, 11:17 Universal Time. The moment arrives with the precision of atomic clocks and the weight of cosmic inevitability. Across the 30 million kilometers separating 3I Atlas from Mars, gravitational fields interact, electromagnetic forces dance, and chemistry forged in alien stellar environments meets a planet that has never experienced anything quite like this interstellar intrusion. The first data packets arrive at deep space network stations with the speed of light, but carry information that travels much slower through human comprehension. Initial telemetry from Mars orbiters indicates normal operations, routine scientific observations, and none of the dramatic electromagnetic signatures that months of speculation had suggested might accompany this cosmic encounter. The numbers scroll across mission control screens with the mundane precision that characterizes successful space operations, each measurement confirming that sophisticated engineering continues functioning as designed. But absence of immediate catastrophe doesn't equal absence of significance. The most important effects of 3I Atlas passage might be invisible to our instruments during the first hours or days of the encounter. Chemical contamination operates on molecular scales that require laboratory analysis to detect. Atmospheric changes might need weeks of observation to become apparent. Even electromagnetic effects could be subtle enough to escape notice until they accumulate into patterns that reveal systematic alterations to Mars' environmental systems. Mission controllers at JPL maintain their professional composure while internally processing the anticlimax of an event that generates data rather than drama. The Mars Reconnaissance Orbiter continues its systematic imaging campaigns, documenting Martian surface features with the same methodical precision that has characterized its operations for years. MAVEN's particle detectors register measurements within normal operational ranges, showing no signs of the charged particle storms that some models had predicted might accompany 3I Atlas passage. The European Space Agency's control center in Darmstadt presents a similar scene of controlled relief mixed with scientific disappointment. Mars Express and the Trace Gas Orbiter maintain their communication links with Earth, transmitting routine telemetry that suggests the Martian orbital environment remains stable and predictable. The atmospheric monitoring instruments that were expected to document dramatic chemical changes instead record variations so subtle they fall within normal measurement, uncertainty ranges. Surface operations teams managing Perseverance and Curiosity report continued rover functionality with no apparent degradation in system performance. The solar panels that were expected to face potential damage from debris impacts continue generating power at normal efficiency levels. Communication systems maintain their regular contact schedules with Earth, showing no signs of the ionospheric interference that could have resulted from electromagnetic chaos in Mars' upper atmosphere. Amateur astronomers worldwide who had coordinated observation campaigns with the enthusiasm of cosmic storm chasers find themselves documenting an event that appears remarkably unremarkable through their telescopes. The dramatic visual phenomena that some had hoped to capture. Auroral displays, atmospheric glows, or obvious debris impacts simply don't materialize in any form visible to ground-based observation. Social media platforms that had prepared for an explosion of dramatic imagery instead host discussions about the apparent normality of what should have been an extraordinary cosmic encounter. The James Webb Space Telescope's infrared observations reveal spectroscopic details that will require months of analysis to fully interpret. But initial processing suggests no obvious thermal anomalies or unexpected chemical signatures in Mars' immediate vicinity. The sophisticated instruments that were positioned to document cosmic catastrophe instead record the subtle data signatures that characterize successful but undramatic scientific observations. But it's precisely this apparent normality that begins generating the most unsettling questions among researchers who have spent months preparing for more dramatic outcomes. The absence of obvious effects doesn't necessarily indicate that no effects occurred. It might simply mean that the most significant consequences of 3I Atlas passage operate on scales or timelines that exceed our current observational capabilities. Atmospheric chemists studying Mars begin the painstaking process of comparing pre-encounter and post-encounter atmospheric compositions, searching for trace signatures that might indicate exotic organic compounds have been introduced to the Martian environment. The analysis requires sophisticated laboratory techniques applied to spectroscopic data collected across multiple wavelengths and atmospheric altitudes. Even minor contamination could have long-term implications for Mars exploration that won't become apparent for years. Planetary defense specialists face the challenge of assessing whether the apparent lack of immediate effects represents genuine safety or simply delayed consequences that haven't yet manifested. The precedent of impact events on other worlds suggests that the most significant changes often don't become apparent until days, weeks, or even months after the initial encounter. Crater formation, atmospheric chemistry changes, and orbital perturbations all operate on timescales that exceed the immediate observation window. The orbital mechanics community begins detailed analysis of whether 3I Atlas passage has introduced any measurable changes to Mars' gravitational environment or the orbital characteristics of its two small moons. Phobos and Deimos, already unstable in their current orbits, could be affected by gravitational perturbations too small to detect immediately, but significant enough to alter their long-term orbital evolution. The calculations required to assess such subtle effects will take weeks or months to complete with sufficient precision. International coordination efforts that had been established to manage potential crisis responses now shift focus toward data sharing and collaborative analysis of what might prove to be the most comprehensively documented interstellar object encounter in human history. The wealth of observational data collected during 3I Atlas passage will provide research opportunities for decades, regardless of whether dramatic immediate effects materialized. But the public reaction to the apparent anticlimax reveals psychological and sociological dynamics that space agencies had not fully anticipated. Social media discussions shift rapidly from anxiety about cosmic catastrophe to skepticism about whether the threat was ever real. Conspiracy theories begin emerging that suggest the entire 3I Atlas scenario was manufactured to justify increased funding for planetary defense programs or to distract attention from terrestrial political issues. The speed with which public interest evaporates following the anticlimactic encounter illustrates the challenges of maintaining support for long-term scientific research when cosmic events fail to provide immediate dramatic payoffs. Educational institutions that had used 3I Atlas as a real-time case study find student engagement declining as the encounter produces data rather than spectacle. The pedagogical value of studying careful scientific analysis gets overshadowed by disappointment that reality proved less dramatic than speculation had suggested. Media organizations face their own challenges in covering a cosmic event that generates more questions than answers. Science journalists who had prepared for dramatic developments find themselves explaining why the absence of obvious catastrophe might be more scientifically interesting than the presence of dramatic effects would have been. The nuanced story of atmospheric chemistry and electromagnetic interactions proves less compelling to general audiences than impact scenarios and planetary disasters would have been. Congressional representatives who had used 3I Atlas as a platform for discussing space funding and planetary defense find themselves in the awkward position of having promoted concerns about cosmic threats that failed to materialize in obvious ways. House Science Committee hearings scheduled to address the encounter aftermath must balance acknowledgement that no immediate catastrophe occurred with recognition that long-term effects might still be developing in ways that require continued monitoring and analysis. The insurance industry begins reassessing its risk models for Mars missions based on the apparent normality of 3I Atlas passage. Premiums that had been adjusted upward to account for potential interstellar object effects might be reduced if the October 3rd encounter proves that such objects pose minimal immediate threats to spacecraft operations. But actuarial calculations must also account for the possibility that subtle effects might create long-term operational hazards that don't become apparent until future missions encounter altered environmental conditions. Commercial space companies with Mars development programs face strategic decisions about whether to proceed with planned missions based on pre-encounter environmental assumptions or to incorporate additional safety margins that account for potential long-term changes to the Martian operating environment. The conservative approach would delay missions until comprehensive analysis of 3I Atlas effects is complete, but market pressures and competitive considerations might favor proceeding with existing plans unless obvious hazards emerge. The scientific community grapples with the challenge of extracting maximum value from observational data that might not reveal its most important insights for months or years. Research teams that had prepared for dramatic immediate results must adapt their analysis strategies to focus on subtle long-term effects that require patient observation and careful statistical analysis to detect. The methodical approach that characterizes good science becomes particularly important when studying phenomena that might not conform to expectations about how cosmic encounters should unfold. Educational curricula that had been revised to incorporate 3-eye atlas as an example of active cosmic threats now face questions about how to present an encounter that produced more uncertainty than resolution. Students learning about interstellar objects and planetary defense might draw incorrect conclusions about cosmic safety if the 3-eye atlas encounter is portrayed as evidence that such objects pose minimal threats. The pedagogical challenge lies in conveying both the apparent normality of this specific encounter and the genuine long-term risks that interstellar visitors could pose under different circumstances. International cooperation frameworks that had been strengthened in preparation for potential crisis management now provide foundations for collaborative analysis of what might prove to be humanity's most comprehensively studied interstellar object encounter. The data-sharing protocols and coordination mechanisms developed for emergency response can be adapted to support the long-term research efforts needed to extract full scientific value from 3-eye atlas observations. As the initial shock of anticlimax begins settling into long-term research planning, the astronomical community confronts fundamental questions about how to interpret cosmic events that challenge our assumptions about what interstellar encounters should look like. The absence of dramatic immediate effects doesn't necessarily validate our models of interstellar object behavior. It might simply indicate that we don't yet understand the full range of ways that such encounters can affect planetary environments. The October 3rd encounter has ended, but the story of 3-eye atlas and its interaction with Mars has only begun. The most significant consequences of this interstellar visitor might not become apparent until future missions attempt to operate in environments that have been subtly altered in ways we're only beginning to detect. The real test of whether we've successfully navigated this cosmic encounter might not come for years or decades, when the long-term effects of interstellar chemistry and electromagnetic interactions finally reveal themselves through changes to Mars that exceed our current ability to predict or control. The data trickling back from Mars tells a story that no one anticipated, least of all the teams who spent months preparing for cosmic catastrophe. 3 weeks after 3-eye atlas completed its closest approach to the red planet, we're facing something far more unsettling than the dramatic scenarios our worst-case models predicted. We're confronting the possibility that this interstellar visitor accomplished exactly what it intended to do, and we never even noticed. The numbers seem reassuring at first glance. Mars continues its orbital dance around the Sun with mathematical precision. Our spacecraft maintain their communication schedules with clockwork reliability. Surface operations proceed according to established protocols. Every metric that would indicate immediate planetary disaster shows readings well within normal parameters. But it's the subtle anomalies hiding within this apparent normality that are beginning to keep atmospheric scientists awake at night. Dr. Sarah Chen at the Mars Atmospheric Research Division first noticed the discrepancies buried deep within routine spectroscopic data. Trace molecular signatures that shouldn't exist in the Martian atmosphere have appeared in concentrations so minute they initially fell within measurement error ranges. But as additional observations accumulate, these exotic compounds show distribution patterns that suggest systematic rather than random introduction to Mars' chemical environment. The molecules themselves represent chemistry that has never existed anywhere in our solar system. Organic compounds with isotopic ratios that could only have formed under the specific stellar conditions of another star system entirely. Their presence in Mars's atmosphere, even at concentrations measured in parts per trillion, indicates that 3-eye atlas deposited far more than just ice and rock during its passage. What makes these findings genuinely disturbing is their persistence. Normal atmospheric chemistry would break down exotic compounds relatively quickly through photochemical processes driven by solar ultraviolet radiation. But these interstellar organics appear to be self-stabilizing through molecular mechanisms that terrestrial chemistry has never encountered. They're not just contaminating Mars's atmosphere, They're beginning to alter its fundamental chemical behavior. The electromagnetic signatures tell an equally troubling story. Mars's weak magnetic field shows subtle but systematic changes that correlate precisely with 3I Atlas passage timeline. The planet's ionosphere, that electrically charged layer crucial for radio communication, exhibits density variations that follow patterns no model can explain using conventional plasma physics. It's as if 3I Atlas left behind seeds of electromagnetic instability that are gradually growing into larger disruptions. Mission controllers managing our Mars spacecraft have begun documenting performance anomalies that seem trivial individually, but create disturbing patterns when analyzed collectively. Solar panel efficiency ratings that drift slightly outside normal ranges, communication system noise levels that increase incrementally over time, star tracker accuracy that degrades in ways that suggest the local electromagnetic environment is becoming increasingly chaotic. The Mars Reconnaissance Orbiter's high-resolution cameras have captured images that require expert analysis to interpret, but which show surface changes occurring at rates that exceed normal geological processes by orders of magnitude. Dust patterns that shift without corresponding weather events, chemical staining on rock formations that appears and spreads according to no terrestrial weathering model. The planet's surface seems to be responding to invisible influences that operate through mechanisms our geology textbooks never described. But perhaps most unsettling are the biological implications that planetary protection specialists are beginning to acknowledge in classified briefings. The exotic organic compounds introduced by 3I Atlas don't just represent chemical contamination. They exhibit self-organization properties that blur the distinction between complex chemistry and primitive biology. These aren't living organisms in any sense we would recognize, but they're active enough to alter their local environment in ways that could persist for geological timescales. The contamination extends beyond atmospheric chemistry to encompass Mars's subsurface water systems. Ice deposits that have remained stable for millions of years show chemical alterations that suggest infiltration by interstellar compounds. The implications for future human missions are staggering. Water extraction systems designed for pure Martian ice might produce liquids contaminated with alien chemistry that no Earth-based purification technology can handle. Underground aquifers that represent potential water sources for Mars colonies exhibit molecular signatures that indicate widespread distribution of 3I Atlas compounds throughout the planet's hydrological systems. The contamination isn't limited to surface deposits where it might be avoided through careful site selection. It's penetrated deep into Mars's subsurface environment, potentially affecting every location where human missions might attempt to establish permanent settlements. The timeline for understanding these effects stretches far beyond typical mission planning horizons. Unlike impact craters or electromagnetic storms, which reveal their consequences relatively quickly, chemical and biological contamination operates on scales that could take decades to fully comprehend. We might not grasp the complete implications of 3I Atlas legacy until human explorers actually attempt to live and work in the altered Martian environment. International space law provides no framework for addressing contamination scenarios involving interstellar objects. The Outer Space Treaty and subsequent agreements assume that cosmic threats will be either natural phenomena that can be studied scientifically or human-caused problems that can be addressed through diplomatic negotiation. Nobody anticipated the possibility of irreversible planetary contamination delivered by visitors from other star systems. The economic implications are beginning to ripple through aerospace industries that have invested billions in Mars exploration and colonization technologies. Life support systems designed for current Martian atmospheric chemistry might prove inadequate if 3I Atlas has fundamentally altered the planet's chemical environment. Habitat designs based on utilizing local resources could become obsolete if those resources have been contaminated beyond safe utilization. Private space companies face strategic decisions about whether to proceed with Mars missions based on pre-encounter environmental assumptions, or to accept potentially catastrophic delays, while scientists attempt to understand what 3I Atlas has done to their target destination. The conservative approach would postpone human missions indefinitely, but competitive pressures and investor expectations create powerful incentives to minimize public discussion of contamination risks. NASA's Mars exploration timeline, carefully planned around launch windows and technological development schedules, confronts the possibility that fundamental assumptions about planetary conditions might no longer be valid. Mission planners who spent years optimizing systems for known Martian environmental parameters now face the prospect of complete redesign based on altered atmospheric chemistry and subsurface contamination that could affect every aspect of surface operations. The psychological impact on Mars exploration teams has been profound, but largely hidden from public view. Engineers and scientists who dedicated their careers to making the red planet humanity's second home find themselves questioning whether that goal remains achievable. The planet they studied and planned to explore might no longer exist in any form that resembles their carefully constructed models and expectations. But it's the information management challenges that create the most immediate institutional stress. How do you communicate to the public that Mars might have been fundamentally altered by cosmic contamination without triggering panic or undermining support for space exploration programs? How do you balance scientific honesty about genuine uncertainties with the need to maintain public confidence in institutional competence? The precedent of previous space exploration setbacks provides little guidance for managing public communications about planetary contamination scenarios that operate on timescales exceeding political and media attention spans. The Challenger and Columbia disasters, while tragic, were discrete events with clear causes and obvious consequences. Interstellar contamination represents a different category of challenge entirely, one that might not reveal its full implications for generations. Congressional oversight committees face the uncomfortable task of evaluating space agency responses to threats that might not become fully apparent until long after current representatives have left office. The political mechanisms designed to provide accountability for government programs struggle with cosmic challenges that operate according to astronomical rather than electoral timescales. Educational institutions grapple with how to incorporate 3I Atlas lessons into curricula that prepare students for careers in fields where fundamental assumptions might be overturned by observations that haven't been made yet. Textbooks that describe Mars as a predictable destination for human exploration might need complete revision based on contamination scenarios that are still developing in real time. The scientific community faces pressure to provide definitive answers about 3E Atlas effects, while simultaneously acknowledging that the most important consequences might not become apparent for decades. Research teams that specialize in planetary atmospheres, astrobiology, and Mars geology find themselves collaborating across disciplinary boundaries that were never designed to address interstellar contamination scenarios. International cooperation in Mars research has intensified as space agencies recognize that understanding 3I Atlas effects requires sharing data and expertise across institutional boundaries. The collaborative frameworks developed for managing potential crisis responses now provide foundations for long-term research efforts that might span multiple decades and require sustained commitment from multiple nations. Amateur astronomy communities that documented 3I Atlas passage continue monitoring Mars for visual changes that might become apparent to ground-based observation. While their equipment lacks the sensitivity to detect molecular contamination, they provide valuable long-term baseline observations that could reveal larger-scale environmental changes as contamination effects accumulate over time. The insurance industry struggles with risk assessment challenges that have no historical precedent and no reliable mathematical models. How do you calculate premiums for Mars missions when the planetary environment might be undergoing systematic alteration by processes that exceed current understanding? Actuarial tables designed for terrestrial risks prove inadequate for cosmic contamination scenarios, that could persist for geological timescales. Commercial space tourism companies that had planned suborbital and orbital Mars viewing missions face questions about whether such activities remain safe if the planet's electromagnetic environment has been destabilized by interstellar contamination. Even missions that don't involve surface contact might encounter radiation or electromagnetic hazards that didn't exist before 3I Atlas passage. The broader implications for human expansion beyond Earth force reconsideration of fundamental assumptions about planetary colonization strategies. If interstellar visitors can systematically contaminate worlds over timescales that exceed human planning horizons, traditional approaches to space settlement might require complete redesign around principles of cosmic contamination management and planetary protection. Future interstellar object detection programs will need to incorporate contamination assessment capabilities that don't currently exist in our space surveillance infrastructure. The discovery of objects like 3I Atlas, years before their closest approach, could provide opportunities for contamination mitigation that weren't available during this encounter, but only if we develop technologies and protocols for managing such threats. The 3I Atlas encounter has revealed gaps in our cosmic threat assessment frameworks that extend far beyond traditional asteroid and comet impact scenarios. Chemical contamination, electromagnetic disruption, and long-term environmental alteration represent categories of interstellar risk that planetary defense systems were never designed to address. Future space security strategies will need to encompass threats that operate through subtle transformation rather than dramatic destruction. As we continue monitoring Mars for signs of ongoing contamination effects, we're learning uncomfortable lessons about the true nature of cosmic citizenship. The universe operates according to principles that don't respect human timescales, national boundaries, or technological limitations. Our survival and prosperity as a spacefaring species might depend on developing institutions and technologies capable of managing threats that exceed our current comprehension and extend beyond our current attention spans. The story of 3I Atlas and its legacy on Mars has only begun to unfold. The most significant chapters might not be written until future human missions attempt to operate in environments that have been irreversibly altered by chemistry forged under alien stars. Whether we prove capable of adapting to these cosmic realities will determine not just our success in exploring Mars, but our readiness for membership in a galaxy where interstellar contamination might be far more common than we ever imagined. In the end, the worst-case scenario for 3I Atlas might not be the planetary catastrophe we feared, but the gradual realization that we're no longer studying the Mars we thought we knew. We're exploring an alien world that wears Mars' face while harboring chemistry that could rewrite the rules of planetary science for generations to come. The Red Planet has become our first laboratory for learning how interstellar visitors can transform worlds without anyone noticing, until it's far too late to reverse the changes they've made. Part 12. The Unraveling Truth. 3 months have passed since October 3rd came and went without the cosmic fireworks that dominated headlines throughout 2025. The world moved on, as it always does, to newer crises and fresher anxieties. Social media algorithms pivoted to different disasters. Congressional committees shifted their attention to terrestrial concerns. Even the amateur astronomy community that had mobilized with such enthusiasm found their interest waning as 3I Atlas continued its journey toward the outer solar system, appearing to leave Mars exactly as it had found it. But in the sterile corridors of NASA's Jet Propulsion Laboratory, in the data analysis centers of the European Space Agency, and in university research facilities around the globe, a different story was quietly emerging. A story that began with anomalies so subtle they were initially dismissed as instrument drift, so minor they fell within normal measurement error ranges, so gradual they required months of patient observation to detect. Dr. Jennifer Walsh at MIT's Mars Atmospheric Laboratory noticed it first. Working through routine analysis of post-encounter atmospheric data, she stumbled across molecular signatures that shouldn't have existed in any database of Martian chemistry. Complex organic compounds with isotope ratios that defied every model of solar system formation. Their concentrations were infinitesimal, measured in parts per billion, but their presence was undeniable, and their implications were staggering. The molecules exhibited characteristics that had never been observed in terrestrial or extraterrestrial samples. Carbon chains with unusual branching patterns, nitrogen compounds with isotopic signatures that could only have formed under stellar conditions, radically different from our Sun's environment. And most disturbing of all, self-organizing structures that seem to resist normal chemical breakdown processes. Initial attempts to replicate these findings in other laboratories met with skepticism and methodological challenges. The concentrations were so low that only the most sensitive analytical instruments could detect them, and the molecular structures were so exotic that standard reference databases contain no matching entries. It took weeks of careful calibration and cross-validation before the scientific community began acknowledging that something genuinely unprecedented had been discovered. The distribution patterns of these interstellar compounds revealed the scope of what 3I Atlas had accomplished during its brief passage near Mars. Rather than depositing contamination in localized regions where debris impacts might have occurred, the exotic molecules appeared throughout Mars's atmospheric column, from surface level to the upper reaches of the ionosphere. The contamination was global, systematic, and far more extensive than any impact-based delivery mechanism could explain. Atmospheric circulation models showed how trace amounts of interstellar material, once introduced to Mars' thin atmosphere, could spread across the entire planet within weeks of the October encounter. The same weather patterns that create seasonal dust storms had efficiently distributed 3I Atlas's chemical legacy to, ensuring that no future every corner of the Martian environment landing site would remain uncontaminated. The electromagnetic implications proved equally concerning as researchers delved deeper into post-encounter data. Mars's ionosphere, that electrically charged layer crucial for spacecraft communications, exhibited density variations that followed patterns unlike anything in the historical record. The changes were subtle but persistent, creating communication windows that no longer matched decades of operational experience. Mission controllers managing Mars orbiters began documenting performance degradations that seemed insignificant individually, but created alarming patterns when analyzed collectively. The Mars Reconnaissance Orbiter's star trackers required more frequent recalibration than normal operational procedures anticipated. MAVEN's particle detectors showed gradual sensitivity drift that suggested exposure to charged particle populations outside their design parameters. Communication delays and signal quality issues, initially attributed to normal space weather variations, began showing correlations with the presence of interstellar compounds in Mars's upper atmosphere. The exotic chemistry wasn't just contaminating the planet's surface, it was altering fundamental properties of the electromagnetic environment that spacecraft systems depended on for reliable operation. Surface rovers faced their own escalating challenges as contamination effects reached ground level. The fine Martian dust that inevitably coats everything began exhibiting different electrical properties, creating static buildup that interfered with sensitive electronic systems. Dust devil encounters, normally routine weather events that rovers were designed to handle, started producing electromagnetic interference that hadn't appeared in years of previous operations. As we stand here in late September 2025, just days before October 3rd arrives with the inevitability of orbital mechanics, we're forced to confront an uncomfortable truth about humanity's relationship with the cosmos. 3. Atlas isn't just testing our spacecraft or our atmospheric models. It's testing us, our ability to process uncertainty, our capacity for international cooperation, and our readiness to exist in a universe that operates according to principles far more complex and dangerous than our brief technological civilization has yet comprehended. The worst-case scenario for 3i Atlas might not be any single catastrophic event we've explored tonight. It might be the gradual realization that we've been asking the wrong questions entirely. While we've focused on impacts and electromagnetic storms, on contamination and orbital chaos, the real test may be whether we can evolve beyond our terrestrial limitations to become a species capable of cosmic citizenship. October 3rd approaches with mathematical precision, carrying with it the weight of possibilities we can barely imagine. Whatever happens when this interstellar wanderer sweeps past Mars, one thing is certain. We'll never look at the red planet or our place in the galaxy quite the same way again. The universe is about to deliver its verdict on humanity's cosmic readiness, and we're about to discover whether we're prepared for the answer. The countdown continues, indifferent to our hopes and fears, following laws that predate our existence and will outlast our memory. In just days, we'll learn whether we've been preparing for the right disaster, or if 3i Atlas has something entirely different in mind for our neighboring world and our species' cosmic future.